Morning, everybody. We'll have the statutory little wait for people to get in.
How's the weather up there in Alaska, Franz?
So we had actually a pretty nice day yesterday, but what's kind of a little disturbing is that we already have discolored leaves. So we are in fall. It's so the mid of August is typically when the nights are getting colder and it feels kind of fallish outside. But usually we don't have leaves turning before late August, early September. So it's a little early this year. But it was very nice. It was a very nice fall evening yesterday.
Yeah, we're moving into the heat of summer here in Southern California.
Yeah.
We escaped for a long time. Like July was pretty mild.
It was surprisingly mild in July. But 38 degrees centigrade is pretty hot. Prediction for today.
What, how much?
38.
That's not, well, that's not particularly hot for Riverside in the summer, I have to say, but it is hot for Pasadena.
Yeah, I mean, we get over 40 sometimes, but it's if it got up to 38 degrees there in Alaska, I think things would all melt.
Yeah, or burn, or both.
Or burn.
Well, that's what happens here too, the burning part.
Well, we don't have any permafrost.
Yeah. Imagine how much methane you could release.
We don't need cows for methane. It's kind of interesting when you walk around, Fairbanks, and you look at some of these lakes. You see them bubble all the time because of thawing out ice wedges and permafrost below, and all that stored carbon that was stored there for a long time being released.
Positive feedback loop, marvelous. That's just what we need.
It's actually something you can measure with SAR. You have a few papers on that. If you can in the winter when the lake freezes over, these methane bubbles, they freeze into the ice and they change the scattering characteristics of the ice, and you can correlate the amount of methane being released to the radar brightness.
You can also measure the deformation associated with thermokarst thawing, right?
Yeah, there's also that. We also have new lakes being formed by then another thing that's related to warming climates. It's the expansion of beavers. So we have beavers migrating north, and we have a lot of beaver ponds, and the water changes the temperature regime, introduces heat into the ground, and we have lots of thaw out of permafrost around those lakes and subsidence in those areas.
Is the water still enough that you could use the double bounce, like water level measurement, like
with a Winsky kind of thing?
Yeah.
You don't usually have as much growth as they have in the Everglades in the water.
Surprising. Not yet, anyway.
Not yet. It's not quite as tropical yet. But get ready, it's the next Hawaii.
I propose that we start when the number of participants in the call gets to 50. We're at 43 right now. I may change my mind if no one joins in the next minute.
There's somebody. I hope everybody's doing good today. Still full of energy after the 3 days of the course. At least one person that's still energetic.
2 people, I would think, maybe. Wow.
Oh, there you go. Exploding hands.
That was just exuberant.
I take it. We have 46 now. Of course, some of those are us.
Yeah, well, maybe we should get started because we do have a packed agenda today and less time set aside for review this morning. I will share my screen just to show you what's coming up today. Okay, so I'm going to start in a little over 20 minutes with Eric talking about SAR missions. It's very important to know the sources of your data, and so we'll go over a mini presentation on what those are and historically have been. Franz will then lead, after a break, an exercise on measuring large displacements of the surface using dense offsets. A slightly different workflow from InSAR, but another tool that we have at our disposal for measuring things with SAR data, and sometimes a very useful one, even for things that you typically can measure with InSAR. Later on, we will have a session on decomposing velocities from ascending and descending data. You can use the diversity of look direction to extract information about the surface movements that is in more useful coordinate systems or more intuitive ones. And so we'll learn how to do that. And then we will hear about the latest developments of ICE, and the next version, which is known as ICE3. And we will hopefully be primed to jump on it when NISAR data is available. And of course, at some point, the instructors of this course are going to have to learn how to use it and teach it. So this is of great interest to the instructors as well. Okay. So we do have some time to see what people have been working on or answer questions. So if you have questions, don't be shy. Get asking. Camilo.
Yeah, how are you? Yeah, so I was just thinking, so far we have been looking at techniques to looking at an interferometric pair or time series, and we have been looking at things to improve the result. Is there any way of calculating an uncertainty map? Like, for instance, we're at the end of the day, we're generating displacement maps. Would it be possible to calculate the uncertainty of those displacement maps? Kind of like what you do when you kriging and you got your estimates, and then you go for this uncertainty map to see how reliable is each piece of information that you have on your. Is it possible with ICE?
So there's two types of uncertainty. There's the two main types are the coherence loss. So we have a measurement of coherence that's always calculated when the ICE calculates an interferogram. That's one quantification of the fine scale noise and loss of coherence, and that affects your ability to estimate the phase, which then is your phase measurement, that is your displacement measurement. The other main source of uncertainty is the atmosphere. And we had the lecture yesterday from Anne about the troposphere and ionosphere parts of the atmosphere. And we can't estimate that from the data directly. Or at least we don't know what, but we can make an estimate of what that is if by looking at an area of the scene where we think there's no deformation. So a lot of times when we have an earthquake, the earthquake only affects a part of the scene, so we can cut out that part of the scene and then look at the statistics of the phase in the rest of the interferogram as a function of distance, and get an idea of what the atmospheric noise level is in that scene. And then there's all the time series analysis methods that Yunjin is going to talk about tomorrow, that also can be used to estimate uncertainties.
Yeah, I think on Friday, I'm not sure if Hyunjin is on. He's gonna show you some of those things for the time series perspective already. For a single interferogram, there is either ways how you can try to formally model it, but the better way is to look at parts of the scene. If you have the luxury, if your displacement is expected to be more localized, you can use part of the scene where you think not much is going on to get an estimate of the noise level. John.
For GNSS specs, they usually report their figures with sigma maps, right? Like the um 2 sigma um uncertainties. So with InSAR time series, are we able to represent that as well in that similar manner, like having plus minus 2 sigma in the plots, or is there a standard way for in the InSAR process?
Yeah, again, I mean, within MinPy, there is the capability to add error bars to your displacement estimates. And as far as I recall from last year, Yunjun is going to talk about that. Do I recall that correctly, Eric?
Yeah.
Yeah.
That's the standard part of the MinPy analysis, is doing estimates of errors. But there's the other type of error that can affect your interferograms is unwrapping errors. And those are actually very more difficult to detect. If you have a time series, then one of the ways to detect unwrapping errors is to do the triangular phase calculation, where you take the A minus B interferogram, the A minus C interferogram, and the B minus C interferogram, and subtract them. They should come out to 0, and if they don't, then there's a good chance that could be either a phase unwrapping error or one of these phase closure errors that Scott mentioned a little bit yesterday, due to the surface conditions. But if you have a patch where the whole area has the same phase closure error, it's almost surely due to unwrapping error. And MinPy actually has a function where they can try to correct for those unwrapping errors by looking at the phase closure, the triangular phase. So Amo Duira, I hope he's pronouncing it correctly, is asking, can ISCE2 be used to process interferograms generated from GMT-SAR? If you've already processed your interferogram with GMT-SAR, then I think ISCE2 isn't really going to help you very much, because they both do basically the same thing. So I think I can't think of a good situation where you would do part of the processing in GMT-SAR and part of the processing in ISCE. Because they use different data formats, especially the metadata. I think it would be quite a lot of effort to convert a GMT-SAR product into a product that ISCE can then work with. If you're asking about putting your products interferograms into MintPy, yes, MintPy can work with interferograms from ISCE or from GMT-SAR or from the Hype 3 gamma or the regular gamma. There's a lot of different data types that MintPy can be used for. Yeah, as Amrit mentions in his response, the GMT-SAR also has a type of SBAS analysis that's I haven't used it, so I don't know what it does, but I think it's fairly similar to MintPy. I've only used MintPy myself.
It could be if you want to sort of dive more into the interferograms you create, while like GMTSAR and ICE are both doing TOPS interferometry using Sentinel-1, there are a little bit of differences. So when Eric went through the TOPS InSAR process, one thing that he talked about was the enhanced spectral diversity, so this very accurate co-registration step. That's actually not implemented in GMTSAR, with the belief that it costs a lot of computational time, and it may not always be necessary to do this additional step. So you could compare some interferograms. I'd be curious now. For a long time, I think the GMT-SAR folks were justified in their choice. The timing of the satellite orbits were really good, and the alignment of images was really good. But more recently, there was the orbit control around Sentinel-1B has been loosened some, and it would be interesting to see if that has an impact on making potentially enhanced spectral diversity processing more necessary. So you could compare some interferograms to see if you see artifacts in one that you don't see in the other.
I know that both GMTSAR and ICE have processors for the ALOS-2 ScanSAR. I think, well, I'm obviously biased because I worked with a postdoc that wrote the software to do the ALOS-2 app in ICE2 for the ALOS-2 ScanSAR processing. He does a lot of extra work to make sure that the subswaths are precisely co-registered in order to make the full interferogram, where GMTSAR just processes the 5 subswaths to get separately and then tries to join them together at the end, and it often ends up that the subswaths don't really match that well. So I think that's a difference between GMTSAR and ICE2 ALOS-2 app, specifically for ALOS-2 ScanSAR data. And since now JAXA has been sending all the ALOS-2 ScanSAR data to the ASF to be publicly available, that's becoming a much more widely available data set. It used to be limited to people that had ALOS-2 PI data projects, but now they're releasing all that ALOS-2 ScanSAR data publicly.
And the advantage of getting it from ASF is that they've halved the file size, right? Like the original JAXA SLCs were like 60 gigabytes each, and I think they're only 30 coming from ASF, which is a nice
that
nice
could be
improvement.
because they only collected one polarization. In the last couple of years, a lot of the ALOS-2 ScanSAR data is only one polarization instead of 2. That makes it half the size.
Okay, maybe I'm attributing things to ASF that not deserved. Stephen.
Yes. Hello, everyone. I wanted to ask a question. Yesterday, we were talking about time series, and what I saw was sometimes we were talking about stacks of SLCs. And if I go on the top stack and I use the time series, you have different workflows. So we have the stacks of SLCs, but also stacks of interferograms. But in which case, it's like, for example, when you prefer to use one workflow respect to another one. Like, for example, if I want to study, I want to do a time series of, for example, faults mechanism. What should I use, depending on probably what you want to do?
Okay, so MintPy, if you want to do an SBAS analysis, you need interferograms, and
Exactly.
so you need to follow that workflow, which is has more steps than the co-registered SLC stack. Software like Dolphin will take, which we haven't seen yet, but we will, takes as its input a stack of co-registered SLCs. So depending on the application and the software you want to use, you might have to use a different workflow.
Okay. Thank you very much.
Yeah, so if you mostly stick to distributed target analysis, so you're looking at filterings. You apply spatial filtering to the phase, and you unwrap the interferograms and so on. This is what MinPy would do. You can form interferograms independently, so you don't have to first co-register the SOCs, because in the filtered multi-looked interferogram, which then has say an 80-meter pixel size, an alignment, a rough alignment of, like, even if you're off by a meter or so, is sufficient to do your time series analysis. If you wanted to mix in point target analysis, so the squeezar or the approach behind Dolphin that you'll see uses both distributed and point targets, then your alignment of the images has to be much more accurate in order to exploit those point targets, because then you don't do any filtering. You're looking at the full resolution data set at these point targets, and that requires excellent co-registration throughout the stack that you're analyzing, and then you have to at first co-register your stack and then work off of that stack. So it depends a little bit on what exactly you're looking for. In an ideal world, if you had unlimited compute power and unlimited time, the approach that Dolphin is using, which is using both point and distributed targets, would probably be the way to go, because it gives you probably the highest density of information. But the benefit of adding point targets is not equally relevant in all places. So it might also be a trial and error. You could do a trial balloon where you process both for a limited time span, and then see, is it worth the effort to go through the full approach.
Thank you very much.
There's a bunch of questions in chat. Oh, people are already responding to those. Gabriela, do you want to ask out loud your question? Or Enrique? Oh.
Well, Enrique can ask.
Yes, thank you. My question is about how can I combine Sentinel-1 C-band and ISCE L-band to generate long time series in the future?
Who wants to take this? I think if you're so you would have to make an assumption that what the two are measuring is the same for most, I think, applications. Like if you think of a seismic application, that is probably reasonably close to be the case. In both cases, you would predominantly see surface scattering in the coherent data set, such that the observations you get from both are similar. You would have to initially process them individually. So you would process a stack of ISAR data and a stack of Sentinel-1 data sets to a displacement time series, and then you could combine the two after the fact.
Yeah, one important caveat is that ISAR is going to be left-looking.
Yep.
And that means that the line of sight direction will be different from all the other satellites that are right-looking. So if it's primarily vertical, that won't be a big effect. But if there's a north-south component, then that north-south component will be in the opposite direction for ISAR than it is for the Sentinel-1 and all the other satellites.
Yeah, and so this means that they may not, and very likely won't, look exactly the same at first. But the upshot is you potentially have 4 geometries. If you have ascending ISAR, descending ISAR, ascending Sentinel-1, and descending Sentinel-1. And so the stuff that Gareth showed you earlier this week about decomposing observations or projecting observations into line of sight, you get 4 line of sights, which may give you a much better handle to come up with your decomposed displacements.
Yeah, I mean, you can imagine having a model which is like a Kalman filtered model. I mean, I don't think there are any freely available codes that will do this for you, but you could imagine if you're tracking coordinates in three component directions, that you could ingest this information into your model and update your model with information from all sorts of different satellites. You would have to interpolate it in time somehow, which is complicated, but I'm sure we'll be developing methods to do this. I've kind of done some combination of ascending and descending data that were acquired on different days like that. You have some interpolation and then you interpolate them onto the same epochs, and then you can look at the east-west and vertical displacements as a function of time. And you could do something like that potentially with 3 components, with the Sentinel-1 and ISAR. But that would be kind of a frontier development. I think we don't really have codes that do that right now.
Yeah, there's a little bit of work. There's a guy called Sergei Samsonov in Canada. I've actually never looked at his code, but he has like a multi-SAR sensor inversion algorithm that he's developed and published. I don't know if the code is accessible, but there are papers out there that he put together.
Yeah, MS BAS.
MS BAS, yep.
So maybe we can answer one last question from Gabriella. She says she's looking at an area that has a very large lake, and should I make any other atmospheric correction, especially due to the fact that there's a lake? The troposphere water vapor is somewhat affected by a lake, but I think if you're you have to do tropospheric corrections in places where you have a lot of troposphere. Won't make a big difference whether there's a lake there or usually the biggest water vapor comes from nearby oceans, and the ocean could be 200 kilometers away, but with the weather bringing the water vapor on land, you could easily, it's usually due to the presence of nearby warm ocean water.
If I'm guessing, I think Gabriella is looking at data from Venezuela, which is quite close to the equator. Might there be ionosphere signals there?
Yeah, she says she's using C-band Sentinel-1, so shouldn't be too much ionosphere, but there could be some. Yeah, close to the equator.
Yeah, in the so you get actually more ionosphere in the evening node of Sentinel-1, pretty much about plus minus 10 degree offset from the geomagnetic equator, where you have slopes in the ionospheric total electron content, and depending on the day, these slopes can be different. So you can get these very large ramps of phase in those interferograms. For ISAR, which is at L-band, so in theory more susceptible to ionospheric distortions, the ISAR orbit was intentionally selected to be a 6 a.m., 6 p.m. orbit to stay out of like turbulent ionospheric delay and high total electron content situations very close to the equator. So this is going to reduce issues in this region to some degree.
Yeah, ALOS 2 has a midnight to noon acquisition time, so it has a greater effect. And ALOS 1 had the worst possible effect with the 10 p.m. acquisitions on the ascending tracks.
Maybe, oh, Alireza, were you done? I said you just took your hand down.
Yeah.
Okay.
There's a quick question here. Is it possible to do processing of tandem X with ICE instead of gamma? ICE does process TerraSAR X and tandem X single interferograms. It does not have a module for making DEMs from the bistatic co-registered SLCs that come from tandem X.
Okay, Eric, I think you're up. We've reached 10:30, and we can
Okay.
carry on answering questions in the chat, but we should move on with our program for today.
I'll start sharing my screen here and PowerPoint. Does that look good?
Yes.
Great. So Oops, I started at the wrong place. Somebody was asking about. Letting me go back. Okay, so I'm going to be talking about SAR satellites, including NISAR. There's been a large number of satellites launched in the last decades. For many years, we used ERS-1 and ERS-2. ERS-1 was actually launched at the very end of 1991, but started acquiring data in 1992. It imaged the first, the most famous, the earthquake with InSAR in June 1992 when it imaged the Landers earthquake in California desert. That's been a very well-studied interferogram because it was just a huge demonstration of how InSAR could be used to study earthquakes. And then, so both ERS-1 and ERS-2 started having problems around the year 2000, 2001. ERS-2, they lost its gyroscopes. So the position of the orientation of the satellite was not controlled very accurately. So the ERS-2 data that was acquired after 2001 may or may not be usable, and it requires extra work to make sure that you estimate what the orientation is. Basically, that was the 2001 is sort of the end of the ERS coverage. The Canadian Space Agency launched a satellite called RadarSat-1 in 1995, and that was then operated for a very long time, 24 years, or not 24 years, it's 18 years, until 2013. And a lot of that data was downlinked at the ASF, so the ASF has some of that data. The Canadian Space Agency worked with NASA. NASA provided the launch rocket, and some of the data was then downlinked to the NASA downlink station. Both of these satellites are C-band, ERS-1 and RadarSat are C-band, and then the next C-band satellite was NVSat. This was launched in the middle of 2003, really started acquiring data towards the end of 2003. Gareth and I worked together on analyzing the NVSat data for the BAM earthquake in Iran that was in December 2003. That was the first earthquake imaged by NVSat, and that was a great satellite for about 7 years until September of 2010 when they changed the orbit. They actually lowered the orbit, so it went from being a 35-day repeat to a 30-day repeat, and they let it move horizontally. So basically, very little of the data acquired after that was usable. The ALO satellite from the JAXA was launched in 2006 and then operated until April 2011. All that data is available from the Alaska Satellite Facility because JAXA sent copies of all their data to ASF for distribution. It has a 46-day repeat. It's an L-band satellite. The disadvantage of that was that it had a limited capacity. The ALO satellite also had optical instruments on it. So mostly they operated the SAR on the nighttime ascending pass. And as I mentioned just a few minutes ago, the ascending track pass was at 10 p.m., which ends up being probably about the worst time of the day for the ionospheric effects in the tropical areas. So some of that ALOS data has a strong ionospheric effect. And the other problem is that they only acquire data at best a few times a year in most places. But it's a good start, and it gives a longer time series in some places. Then there's the X-band satellites, the DLR, and the commercial company, which has changed several times. It's now part of Airbus. Built and launched the TerraSAR X satellite in 2007, and then they launched a second satellite, Tandem X. So they actually fly very close together, so they can be used to acquire data simultaneously in what we call bistatic, where one satellite sends out a signal and it's received at the other satellite. That allows you to make a very high resolution DEM. That's why it has the name DEM in the Tandem X satellite name. And that's then they did a full global coverage of to collect the data to make a DEM that's now available for free from Copernicus, the European Copernicus global DEM at 30-meter resolution. So that's quite a outstanding data set. Somebody was asking just a minute ago whether, ICE can process the TerraSAR X single interferograms, but it does not have functions to process the bistatic data to make DEMs. Another big source of X-band data, 3-centimeter wavelength, is the Italian Space Agency. They launched Cosmos SkyMed satellites, a total of 4 satellites in the same orbit in a constellation between 2007 and 2010. And because each satellite has a repeat of 16 days, but then because they had 4 satellites, they had time intervals of 1 day, 4 days, 7 days, 8 days. So there's a lot of data that was acquired with short time intervals. But they have not made that data available openly. They made it available through a number of calls for scientific proposals. I participated in that in the past, but I haven't done that recently. So that data is some places it's available through the super sites programs over typically volcanoes and some of the major fault systems where the Italian Space Agency supplies the data. Same thing with TerraSAR X. TerraSAR X is also, because it's a public-private partnership, the DLR can't give away all the data to everybody for free because the Airbus people want to sell it. And that's, well, some of the data is available through the Super Sites program. The Canadian Space Agency worked with the company, what's the name of the company?
MDA.
MDA, yes. To build the RadarSat 2 satellite. MDA built the satellite, and even though the Canadian government paid for a lot of the cost of developing it, they gave the satellite to MDA to operate as a commercial satellite. Some amount of data is available for public use and from the Canadian Space Agency, but in general, that a lot of the RadarSat 2 data has limited availability. But it was launched in 2007 and it's still in operation. So it's a good source of data for some of the time intervals when there were gaps between the ERS-1, ERS-2, NVSat, and Sentinel-1. What's going on here? Oh, I think it's switching back and forth in focus between the Zoom and the slideshow. There are some other spacecraft that I should make a quick mention. The United States, NASA was actually the first civilian radar satellite. It was launched in 1978. already almost 50 years ago. It only lasted for 110 days. It was an L-band satellite. NASA likes L-band, and but the data was only the technology wasn't very advanced in those days. They didn't have an onboard recording system, so they could only collect data where they were able to send the data down to the ground immediately. So there's very limited coverage. But the ASF has now also made all of that data available. There was a previous JAXA earthquake satellite, JRS-1. That data wasn't very good, but it was there. And then there was the space shuttle mission, shuttle imaging radar mission C. They operated that they flew that twice in 1994. They flew the space shuttle very accurately so that they could make a 6-month repeat between the April and August, September flight, which allowed 6-month interferograms. And then they also put during the October flight, they set it up to do 1-day repeats for about 4 days. So there's a small amount of data acquired by this, but one of the big advantages of this mission was that it actually had 3 different radar wavelengths. It had X-band, C-band, and L-band, all operating simultaneously. I actually got my start doing interferometry with some of this source C data. I think is the Circia data also available at ASF now? It was at the Eros data center at one point. I think it's at ASF now. Anyway, it's
we have all the recoverable Circia data is available and processed to SOCs and also to a quasi geocoded data product. It's not very accurate because the orbits weren't great.
Great.
Those are available through ASF.
Yeah, the most places they only they were concentrating on high resolution, so we had very high resolution, but only for a 20 kilometer wide swath. So you get these little narrow strips of data in a few places around the world. So the big thing that most people use nowadays, or one of the present generation of spacecraft, is Sentinel-1. Which is supported by the European Union under the Copernicus program. It's kind of a little bit of an unusual arrangement. The European Union pays the European Space Agency to build and operate the satellite, but it's still owned by the European Union under what they call the Copernicus program. It's a minor detail, but it makes a difference who's paying for it. So Sentinel-1A was launched in April 2014. It didn't reach its final orbit until October 2014, so they didn't really acquire any data until late 2014, and then they had some time to get their whole ground data system working. So there's not much Sentinel-1A data until around March of 2015. But then it's still operating today. It's been operating for collecting data for more than 10 years. And that's a great data set that's outstanding. The satellite's not in the best health. It has occasional problems and it's running out of fuel, but that's why they're getting ready to launch Sentinel-1D later this year. Sentinel-1B was launched in April 2016. It stopped working in December 2021. So after December 2021, they were back to having only one Sentinel-1 satellite for several years, 3 years, more than 3 years. Sentinel-1C was launched in December last year, and they declared it operational in March of 2025. So now they're back to having 2 Sentinel-1 satellites, and they plan to launch Sentinel-1D. The satellite's all built. They're just getting the last details worked out, tested, and they hope to launch it by the end of this calendar year. And at that point, they're going to deorbit or decommission Sentinel-1A, which is past the end of its planned lifetime. The JAXA satellite ALOS-4 was launched in May 2014, almost the same time as Sentinel-1A. It's also still in operating, but also getting old and having some onboard resource limitations. They've reduced the number of acquisitions in the last 3 or 4 years. It's an L-band satellite. Unlike the first ALOS, it has a 14-day repeat, much closer to the same repeat as Copernicus and ISAR. So it's a short repeat, but it also suffered from the same a lack of capacity to acquire data in some places. So the ALOS-2 had 2 main modes. It has a strip map mode that has a narrow swath of 70 kilometers. And because the orbits are about 250 kilometers apart, about 200 kilometers apart, it actually takes 3 of those 70 kilometer wide strip map swaths to cover the full area. That means that in order to cover the whole land surface, they would need to come back 3 times in order to just get 1 image of the land. And that's with that strip map mode. So a lot of the time they operated ALOS-2 in a ScanSAR mode, which is a very wide, basically 5 of those 70 kilometer swaths combined to give a 350 kilometer wide swath. The ScanSAR is a little bit similar to the TOPS mode used by Sentinel-1, but it has some different characteristics, so it has a different processor in ICE. And now JAXA started sending all the ALOS-2 ScanSAR data to the ASF for the ASF to make it available publicly. I don't know what amount of the data is available now, but I think it's increasing rapidly. They're only making the ScanSAR data available for free because the JAXA also has a public-private partnership for selling the strip map data. There was an Indian satellite, ISRO RISAT-1, was launched in 2012. It's a C-band satellite, fairly similar to ERS-1 with me, but there's some availability of data. So I'll talk more in a minute about NISAR that was launched last month with a 12-day repeat and the S-band and L-band radar wavelengths. This is just a quick what are we doing for time? Speed up a little bit. Sentinel-1A does have a strip map mode. They don't use it very often. Sometimes they use it over oceanic volcanoes where there's no need for a wide swath. The strip map mode of Sentinel-1 can be processed by the ICE2 strip map app processor. But the main mode they use almost all the time is TOPS, the wide swath, 250 kilometer wide swath that we use, that we discussed in the TOPS app and TOPS stack processors. As I mentioned earlier, ALOS-2 has actually 3 different modes: strip map, ScanSAR, and Spotlight. It is possible to process all 3 of these using the ALOS-2 app in ICE2. And then there's a stack processor, ALOS stack. And it works quite well. I mean, I'm biased because, as I mentioned earlier, the postdoc working with me, Shunran Liang, wrote these processors while he was here at JPL. So I think they're great. The RISAT data can be processed if it's strip map data. Other new spacecraft include the Argentine Space Agency SAOCOM-1. They launched SAOCOM-1A in 2018, SAOCOM-1B in 2020. It has a 16-day repeat, but then because they have two, they do 8-day repeats. It's L-band sensor. They have a TOPS mode for getting wide swaths, but it's not interferometric capable. So the only interferometry you can do with SAOCOM data is with the strip map data, but it can be processed with strip map app in ISCE. Japan, JAXA launched a new replacement for ALOS 2 called ALOS 4 a year ago. It's also it's in the same 14-day repeat orbit. The strip map data from ALOS 4 can be combined with the strip map data from ALOS 2. The ScanSAR data from ALOS 4 is not compatible with the ScanSAR data from ALOS 2. We haven't gotten any ALOS 4 data here at JPL yet, so I haven't had a chance to test this, but I saw earlier this week that Francisco Delgado got some ALOS 4 data and was able to process it with StripMap app because it was StripMap ALOS 4 data. The Italian Space Agency has launched a second generation of Cosmos Skymen satellites. I think I need to they have, I think, now launched all 4 of the second generation. Some of their first generation Cosmos Skymed satellites are have been decommissioned. They're all X-band, and again, the data has limited availability, but I think it's they may be providing it to some science data grants. The Canadian Space Agency worked with MDA to launch a RadarSat constellation mission in 2019. It has 3 satellites in the same orbit. Each satellite has a 12-day repeat, but then because there's 3, that reduces the time interval to 4 days. The RadarSat constellation satellites are simpler than the RadarSat 1 and RadarSat 2, and they have less capacity, but they do, but between them, acquire quite a lot of data, mostly over Canada. On its Canadian satellite, they mostly cover Canada, and it's C-band. There's other satellites. South Korea launched an X-band satellite called CompSat 5. The Spanish Space Agency launched a satellite called PAS. It was basically a copy of TerraSAR X, and that it's in the same orbit as TerraSAR X, and it has then a 4 or 7 day repeat with TerraSAR X. They're fully compatible. And in the same orbit, so they can be combined together. The Spanish Space Agency has been giving data to some scientific proposals. We've been getting some data from that. Then there's the what we call the new space satellites. These are the relatively small to very small satellites. Capella, ISCE, and Umbra are the biggest ones. There are some other ones. Most of these are, so ISCE has had some satellites with operating in a InSAR capable format. Capella says they're adding InSAR capability. Umbra also says they're planning to have InSAR at some point. they're all X-band satellites. They generally operate either, so Capella and ISCE have strip map modes and spotlight modes. Umbra only operates their satellites in spotlight mode, so you get very extremely high resolution for very small areas, but not very much coverage. And these are all fully commercial satellites, so people buy the data to do various things. The Umbra company has been making all of their data available after somebody buys an acquisition over a given area. I think within a month, they put it online and give it away as an open archive for anybody to use. But for InSAR, it's not there yet. Umbra actually has such a high, their very high resolution spotlight mode has 16 centimeter pixel size. So it's incredibly high resolution compared to some of the other X-band and L-band satellites. So I want to cover a little bit about ISAR. It has a lot of the main scientific objectives are measuring ecosystem structure, including biomass globally, measuring global ice motion, ice dynamics, measuring surface deformation. So for solid Earth and purposes. And it was launched on July 30th, just about 3 weeks ago, where they did the final deployment last Friday of the boom and reflector. And they're getting ready to turn on the radar this week. So they'll be testing that for the next month and a half. And we expect to have the radar working very soon. They won't reach the final science orbit until sometime in September. So they can't produce the full images until it reaches the final science orbit. But the plan is to do a very fast commissioning and start science operations 3 months after launch. So basically, beginning of October. No, the beginning of November this year. There's many services. All the data is going to be available through the Alaska Satellite Facility. The data is all processed and stored in the Amazon Cloud, AWS, and the cloud-based data tools will make it easier to have access and processing for this data. We will be doing more tutorials later about how to work with ISAR data. ASF has done some preliminary early adopter workshops that are available online. What is it? So ISAR has 2 wavelengths, the L-band radar wavelength, 24 centimeters. The S-band is around 10 centimeters. The S-band data is going to be downlinked and processed in India at the ISRO facilities and available from ISRO. The L-band data is downlinked through the NASA facilities, including at the receiving station there in Fairbanks. It's quite impressive. It's a huge amount of data. It has a 240 kilometer wide swath, and it's going to be turned on all the time that it's over land. Unlike all the other previous satellites, it was designed with the capacity to be able to be acquiring data over land all the time, everywhere. So this is going to be a huge new data set starting in about a month, 2 months from now. It's a 12-day exact repeat. That means they're going to acquire data every 12 days, but they're also going to acquire data on both ascending and descending. So should get a full image of the land surface of the Earth twice every 12 days from the ascending and descending. So the resolution of ISAR is it depends on what mode. It has several different modes. They're all this sweep SAR, which is sort of like strip map, but gives a wide swath of 240 kilometers. It has different resolutions because of different range bandwidths. So it goes from 3 meters to about 10 meters in the range direction for the resolution, and the along track resolution is 8 meters. That's basically determined, or it's actually closer to 6 meters. It's just basically half of the size of the radar antenna reflector, as expected from synthetic aperture radar. The NASA minimum mission requirement is that it operates for 3 years. The system is fully fueled and has resources to last for much longer than 3 years. But NASA calls it a 3-year mission just so they can declare success after 3 years. We expect it to last much longer than that, unless some crazy people decide to turn it off. And this thing down here about the duty cycle, that's how we get this full global coverage, is the ability for the ISAR satellite to be on for 50% of the time that it's flying for each orbit. And it's lift looking, so it's going to be getting much better data over the Arctic, at the Antarctic, almost the whole Antarctic continent, except for a small hole near the pole. But it'll get somewhat less coverage in the Arctic Ocean, where you'll have to use Sentinel-1 or RadarSat constellation. This is a map of showing the observation plan. Most of the Earth is going to be in this background land mode, either the brown mode for the tropics or the green over. That's a 20 megahertz range bandwidth, a dual polarization that has the 10 meter range resolution. Over the tropics, to save data volume, they are only going to only acquire a single polarization on every other orbit to reduce the amount of data downlink. We got a special grant from the Congress to collect higher resolution over North America. So over North America, under this satellite needs working group, we got extra capacity to collect 40 megahertz over almost all of North America, except for these blue areas where they're going to be collecting quad pole. That's the 4 polarization modes, to look at details of how the 4 polarizations are affected by the especially agriculture areas, and up here in Alaska for permafrost and other things. And then there's also the capacity to turn the different modes as it's going along. So there's actually a plan to get higher resolution 40 megahertz data over urban areas in many parts of the world, especially South America and Africa. And then over some of the glaciers like Patagonia, the Alps, and some other places. The S-band data is primarily going to be acquired over India. This region here that's shown, the India and adjacent countries are going to be covered with L and S acquired simultaneously. And then there are some additional places where the S-band data is going to be acquired, or shown by these boxes here, we have a calibration and validation site here in California, so we're getting the L and S band there. There's another calibration site here in Oklahoma where they're also going to be acquiring the S band data. Oh, and then there is this 80 megahertz mode it has a much higher resolution. It's 3 meters in ground range, but it only gets half the swath. So instead of a 240 kilometer wide swath, it only has 120 kilometer wide swath. And they're going to do that in places along the coast of Antarctica and Greenland to get the extremely high resolution to be able to measure the velocities of the extremely fast moving ice in the output glacier ice streams in the glacial areas. So that's the summary of what NISAR is going to be doing. These are the products. The key thing is that NISAR is going to be making the level 2 products, the geocoded and multi-looked polarimetric products. They're going to be making geocoded SLCs that you can immediately make into interferograms without doing any processing. And they're also going to be making multi-looked and geocoded unwrapped interferograms. That's why we covered the ARIA Sentinel-1 geocoded unwrapped interferograms, because those are very highly similar to the NISAR geocoded unwrapped interferogram products. And there is one level 3 product that's going to be produced globally, and that's a soil moisture product. We got an extra allocation of funding from Congress to do a soil moisture map of the whole Earth from NISAR data, and that'll be made as a level 3 product globally at 200 meter resolution. That's this extra product over here. It's a level 3 product that was supported by the Satellite Needs Working Group extra allocation. Then there's also the Opera project is going to be producing some of their Opera products from the NISAR data that they're presently producing from Sentinel-1. They're going to make a global surface water extent product, a global disturbance product, and North America a deformation product from NISAR data. These are the websites. There's sample data sets in NISAR format that people can use to test their software. It's all coming in this NISAR HDF5 format. It's the same as the ARIA Sentinel-1 format. All the specifications are here. There's the open source software, all of the actual processing software, all the way from the level 0 to is available on GitHub. This is the first open science mission. All of the processing software is available. If you really want to go back to the raw data of level 0 and process it yourself, the data is available. It's using ISCE3. That's the InSAR Scientific Computing Environment Enhanced Edition. So it's not going to be processable with ICE2, but with ICE3. We are also releasing the science algorithms that the NISAR science team is using to do the calibration and validation. And those are online as well. And then there's Jupyter notebooks that the ASF has started releasing, and then we'll expect to be making more courses either through the RSET program or possibly other venues for in the near future once we actually have actual NISAR data. So I think that's all we had for that. I'm sorry I went over a little bit.
Only about twice as long as your time slot. But it was
Yeah,
useful, important information. We didn't want to stop you in full flow. I think we'll move on straight on to Franz.
Oh yeah, okay, we can do that. So no break for you.
No break.
So what we'll do next is we look at larger offsets. So we'll look at a separate way of estimating displacements, especially when they're very large. What I encourage you to do now, I'm going to show you a few slides, is to fire up your OpenSAR lab machines while I'm talking, so that we're all ready to go as soon as I'm done belaboring everything on a few PowerPoint slides. So please start up your machines, and I'm going to show you a little bit of content real quick to set up the lab we'll do afterward. See if you see my screen. You should see my PowerPoint deck up. Do you?
Yes, we do.
Okay. So real quick about template matching or sort of offset tracking. So the question is, why do we need this concept for motion map, a second way for motion mapping at all? And it is because for InSAR there is a limitation to sort of the maximum motion that you can estimate unless you do something specific. So if pixels move too much between two scenes, they won't overlap anymore. Once the two data sets are, if you do a broad co-registration of two data sets, say if you have a situation like shown here on the left-hand side where you have a fairly narrow moving feature, like a glacier feature in this case, and most of the scene otherwise is stable, you would co-register the two scenes to the stable parts. And if the moving parts are moving too much, you will lose coherence in these places. For Sentinel-1, if you think that you would create like an 80-meter interferogram, then there's a maximum surface motion that you can allow for, and it's about 24 meters per year is the maximum motion that you can accommodate without losing coherence. You could potentially try to recover from that by doing very fine scale co-registration to recover the coherence, but there are also other ways to then measure these very large motions and approaches that are actually more suitable for these large motions. So one of these large motions is one on Malaspina Glacier in Alaska. It's a very beautiful glacier should you ever fly over it on a clear day. Or you can also look at landsat scenes. It's pretty nice. It is fairly fast flowing, and so what you see here is sort of a time series of this displacement on 3 points of that glacier, where you can see that it exceeds that sort of motion limit in a lot of places of the glacier, and would decorrelate in InSAR. So lots of surfaces do move at rates higher than that. This was supposed to be an animation. Well, I'm not sure why it's not playing. We have to click play. Here we go. Move fast enough for InSAR to not work. Glacier motion is one of those. So template matching or offset matching using cross correlation is used a lot for looking at glaciers. But there's also sea ice motion that you can imagine can be pretty substantial. And even some large earthquakes have potentially motion near the fault that exceeds what can be captured using InSAR. And there's lots of relevant information. This is an animation that was done by Brian Reel, looking at time-dependent velocities of Jakobshavn Glacier. And you see all these like variations that you may want to capture, and you may want to have techniques to measure them. And so we'll be using feature tracking. There's a variety of different terms out there to describe these approaches: template matching, feature tracking, speckle tracking, and so on, to estimate motion velocities, in our case, actually off a glacier, and not just the velocities, but also the direction of motion. So there's a number of reasons and use cases why you may want to apply feature matching techniques. So the main one that we'll be looking at is sort of the second case, where you may want to take images from different times to look at terrain displacement, sort of movements on the ground. But they also used extensively, actually maybe more so, in stereo matching, if you have images that are not taken necessarily at different times, but potentially from different viewing geometries. And you want to find matching points in the two scenes to estimate their 3D their 3D coordinates. And so stereo parallax matching and tie point extraction is something that uses feature matching in stereo processing. You may also have applications where you have data from different sensors that you want to align using co-registration or cross-correlation techniques. Also for DEM matching, which is sort of the same case as this first use case. So there's different ways how image matching can be performed. First of all, you can apply these matching techniques either on the original images or on some sort of image derivative. I think it should be shown here on the right-hand slide. So for instance, this is an optical image of a glaciated terrain. So you see the glacier here, you see the center moraine of between those two glaciers. You could either use the original data like this, or you can use a derivative like, say, the image gradient or image edges for matching. And so the image gradients have the advantage is that they are better at highlighting localized structure. And structure is really good if you want to robustly match one image chip to another. The downside of some of these derivative approaches is that they also can highlight things that you're not as curious about. For instance, here in this optical push broom scanner, there's some radiometric offsets between the different lines of the scanner that you can also see better once you create a derivative, and they may lead to errors and distractions in your matching approach. So there's upsides and downsides to these methods. Then, so once you have created some sort of an input data set, you can then use either area-based methods or feature-based methods for tracking. Feature-based meaning that you first extract geometric features. That could be rectangle shapes, it could be point shapes, lines, and then you try to track these features over time. The other approach, area-based, is that where you basically take an image chip from one scene and then try to find the same image chip on the other scene, and then you basically look at intensity of the scene or intensity patterns to find that same chip again in image 2. And then for area-based methods, which is the one that we will be looking at today, there's then two ways how you can implement them. You can implement them spatially in the spatial domain, and you can implement them in the Fourier domain or the frequency domain. Frequency domain approaches have benefits in terms of the sort of processing speed. It turns out cross correlations are much more efficient to do in the spectral domain than in the spatial domain. But that's an implementational detail that we won't worry about too much today. And then for these area-based processing methods, there are different techniques such as cross correlation, least square matching. What is it called? Crap, I forgot the name now. Doesn't matter. But we'll be looking at cross correlation specifically because for the data sets that we are looking at, cross correlation is a sufficient approach for feature and object matching. Yes, so we look at cross correlation. So cross-correlation is a very powerful tool to find image content in an image. It's a so-called template matching approach where you first take a template segment from one scene, and then you try to recover and discover that particular template in the other scene, and then measure the offsets between the template in the original scene and that same template in a comparison scene. There are some key assumptions for which cross-correlation is applicable. The key assumptions are that the images that you're comparing, they are supposed to only differ in translation, in image brightness, and in contrast. So those things we can cope with. What cross correlation is not great at is if there are differences in scale between the two scenes, or if there are nonlinear distortions between the two images. In some ways, this implies that we're looking at data sets that have the same physical resolution as input. And we also look at data sets that are acquired with a very similar geometry, such that there are no linear distortions between the two scenes. You can imagine if you look at two sort of a mountainous terrain from two different, significantly different look angles, then there are distortions in those two scenes that are not the same, and that can throw off cross-correlation methods. So in our case, we are mostly looking at repeat images acquired with reasonably similar geometries so that these key assumptions apply. And as mentioned, it's a template matching technique. So we find the location of a small template patch within a larger second image. And usually the size of this template is significantly smaller than the size of the total image. And so the goal of cross-correlation is we have two input data sets. We have the total sort of a input image that we're looking at, and we have a little template patch, a G2, and we want to find the offsets in 2 dimensions in sort of the line and sample direction between those 2 patches. And so we allow for this geometric transformation here. So we estimating the parameters of that geometric transformation that transform the coordinates or measure the offsets between the image template coordinates and the overall image coordinates. And so this offset is that offset UV. So that's the variable that we're interested in. Additionally, we can cope, as mentioned earlier, with some radiometric transformations as long as they are linear. So we can deal with sort of an overall brightness offset between those 2 scenes, which we can model in the cross-correlation approach with additional parameters. So we can allow for this linear transformation between the radiometric properties of the input scene and the radiometric properties of the template by estimating these additional 2 parameters. Mostly the way we deal with radiometric offsets is by typically not using the original scene for cross-correlation, but instead using a derivative of that scene, such as a gradient calculation. First, the gradients are often less sensitive to radiometric offsets than the original scene itself. And so again, the task and the goal is to estimate these offset parameters U hat and V hat. There's different ways how you can calculate sort of a similarity metric between the template and scene content. We will be using this normalized cross-correlation approach, which is the established method to use these days. There are different ways how you can physically implement that to make the cross-correlation estimates high quality, ideally sub-pixel quality, but also to make it performant in terms of time. So we want in the end to have many templates for that we discover in the scene and compute cross correlations for. And so what we do is we basically calculate this offset for which the cross correlation is maximized. So basically we have a template, we move that template over a scene, we calculate a cross correlation for all of them, and then we find the peak of this cross correlation, and we assume that that is the correct position of the template. And then we can estimate those offsets. We can do that more efficiently than by looking through the full resolution scene. What sometimes folks apply is sort of an image pyramid approach, where you first create several levels of downsampled versions of the original scene. You start with the lower resolution version to estimate offsets at a lower resolution, and then you use those estimated offsets to narrow down your search space at higher resolution pyramid levels, and that can let you accelerate your search quite a bit. Otherwise, how you can do it is you can bracket the amounts of motion you expect. So the approach that I show you uses this approach where we provide some assumptions for how large the motion could have possibly been between those two images. And so we don't actually then search the entire scene to find matching templates, but only a neighborhood within that search radius we allow. So we assume that probably that glacier didn't move kilometers within a few days, but we know roughly what kind of motion we would expect.
Hello,
Eric, did you have a question?
I'm fine. How are you?
Oh, there you go. So other things we can do is we can, to achieve subpixel offsets, is we can calculate cross correlations at integer pixel offsets. So here's an example of what a cross correlation landscape would look like. So we put the template here, we calculate the cross correlation, we get a certain value, we move it to the next pixel, we get a certain value, and so on. And we see this value increase as we get closer to the right position of the template, and then that correlation drops off again. Initially, the highest correlation we might find for this pixel location, this would be an integer pixel location, but we often want to know the offsets at a subpixel level. So what we can do is we can fit functions to these offset measurements and then find a subpixel location for the very likely best fitting offset this way. Other approaches you can also use is you can do very strong oversampling of the data set to even further refine this offset estimate. And as mentioned, implementation-wise, we often don't implement this cross-correlation approach in the time domain because it's very, very time-demanding to perform this process in the time domain. So instead, we often use a frequency domain approach where sort of cross-correlation, which in time domain has many thousands of steps, would boil down to a single calculation step, and then speeds up the process quite a bit. So cross-correlation is the main approach that we'll be looking at today. Just for completeness, there are many other approaches available to do identification of objects between scenes. There are feature-based approaches that are being used a lot, especially if your two scenes may not fulfill the requirements that cross-correlation needs. So if scenes have different exposure, a different pose, vastly different observation geometries. You see a sample down here of what that can look like. So if you've been looking into like drone-based stereo mapping, for instance, and you use techniques such as structure for motion, they actually don't end up using cross-correlation anymore because they deal with data sets that may have very different pose. And so they use other techniques such as SIFT, scale-in invariant feature transforms, to robustly find matching features in scenes and measure their offsets. Just a few thoughts on pre-processing steps and error sources. So often when we do feature matching, we do a little bit of image enhancement, such as gradient calculations, potentially also some noise filtering if you have very noisy data sets. So the approaches that I will show you, they internally do, they are based on gradient images. So they do a calculation of gradients first. Some methods employ this pyramid approach to speed up processing. We'll be looking at auto-rift, and that actually does not employ pyramid approaches in this case. You may do some initial image alignment. We also won't deal with that today. We'll be expecting that the input scenes are already geometrically aligned so that in places where the offsets are zero or where there's no motion, we would expect the offsets to be zero. If you have data sets that are poorly aligned, you may want to first do a coarse grid image alignment and then do a secondary high resolution offset analysis to measure velocities on the ground. And then there's a lot of post-processing that you can do. Sometimes you can run into outliers when you do image matching using cross correlations. These can happen, for instance, if you have repetitive surface structures. You could imagine that you have agricultural fields or so in a SAR scene where you have repeated structures, or an urban environment in the US where you have, building blocks that may look very similar in your data set. So you can run into mismatches this way. Also, if there's poor contrast in a scene, you may get mismatches. So in post-processing, you can do outlier and filtering approaches to clean up your results in some ways. These can use some geophysics, these outlier approaches. For instance, down here, you see that this is a sea ice tracking method, which allows only certain distortions of a two-dimensional grid to sort of catch and remove geophysically unreasonable outliers between scenes. You can also use information on streamlines, like for a glacier. You may know that you expect motion to go in only very specific directions, and you can use that knowledge also to post-process your mapping results. Let's see, your mapping errors, image misalignments are sources of errors. Cross-correlation can run into issues. All of these matching approaches can run into issues in areas where you have very low contrast. And I may actually ask you a question about this later. If you think of glacier surfaces, in some places you have more contrast. Actually here, this is not too bad of an area where you have crevasses and flow structures that you can identify. But if you were to go further upstream on a glacier where there's snow cover, you may have very uniform surfaces that may not be very conducive to matching. And especially for those, SAR can actually have some advantages, and we can talk about that during the lab. And in optical data, of course, cloudy areas when you actually can't see the ground are a challenge. Cross-correlation, you can actually theoretically calculate how accurate you can estimate offsets using cross-correlation. So here I'm doing a ballpark estimation using for SAR images specifically. SAR images lend themselves really well for template-based offset matching because SAR images have speckle noise. And so if the speckle noise stays coherent between repeated scenes, it's a really, really nice way to track offsets very accurately. Because if you've looked at speckle noise ever, it's a very noisy pattern. And the more noisy the pattern is, if that noise stays the same, the more accurate you can measure offsets between scenes. So that's really good, especially if you have otherwise fairly featureless terrain. So going back to this, to sort of higher levels in Greenland, for instance, where you have snow cover on the landscape, the speckle pattern in the SAR scene allows you to measure offsets even in those areas, assuming that the speckle pattern stays reasonably coherent between multiple time steps. And then you can actually calculate how good of an estimate you would expect. So this assumes that the speckle pattern is useful for offset mapping. Then you can calculate with what percentage of a pixel you can estimate offsets depending on how coherent these speckle patterns remain. And if the speckle patterns remain mostly intact, you can estimate offsets to a fraction of a pixel robustly. And you can estimate it by a factor of 2 better if you use both the amplitude and phase for offset mapping or the complex data for offset mapping. But still, even with an amplitude-only approach, you can get very robust subpixel estimates. And then if you do some multi-looking, basically coarsen your resolution cell, then this estimate gets even better. And so just before the preparation of the lab, so while you spin up your lab, just a little example of what that can look like. So we'll be using an algorithm that was developed as part of a project called ISCE in this particular exercise. This algorithm is called AutoRift, and it's implemented adjacent to ICE. It uses ICE features during the processing. We'll be also installing AutoRift when we go through the notebook. And it's being used for doing global ice velocity mapping using feature tracking. And it uses the same approach to do feature tracking, not only from Sentinel-1 SAR data, but also from optical data sets all the way back to Landsat 5. And so ISCE has created a really long time series of displacement going all the way back to really the early days of Landsat. So in this case, I'm showing you only 2013 to today for Malaspina Glacier here, but the data record goes back further in time. And by combining all these data sets, you get really, really dense information on the velocity of the glacier. So these different colored lines, there are 3 points on the glacier, but they're really put together from multiple sensors, Sentinel-1, Landsat, and Sentinel-2. And once the offsets are estimated, you can very nicely combine data from these different sensors to get a coherent and a useful time series from it. And so we'll do the lab exercise first, and if you have time left, or maybe as a homework exercise or sort of for your own edification, you can then go to the actual ISCE Live page and explore some other sites. So we'll be looking at a glacier, we'll be calculating offsets ourselves, and then later you can poke around in the automatically created offset files on a global scale to find some cool offset estimates. I don't know if you have any questions at this point. I saw some questions pop up that were answered. Otherwise, let's see. Let me see my audience here. If you could give me all a thumbs up, making sure that you're all ready to go with Open Science Lab. Are you all on the platform? So before you get going with the notebook, so we'll be actually doing something a little bit different with this notebook. In this particular notebook, we will not use the Earthscope InSAR kernel that you've been using so far. So I'm going to use this exercise here real quick to show you how you can build your own kernel using YML, also called YAML files that have descriptions of the software that you want to install. So if you are on the OpenSAR Lab environment in your home folder, you see a folder in your environment on your instance that's called Conda environments. And so please, I encourage you to pay attention to what I'm doing now so that you can successfully run the code. So please all go to that folder called Conda environments, double click that. And you should see something like this, where you have a notebook here that says create Conda environment. So we'll run this notebook here in a sec.
Excuse me?
And yes.
We cannot see your screen. It's still the presentation.
Oh, damn it. Thank you for telling me that. I shared only the screen. Well, that doesn't help much at all if I do that. Let me share my notebook. Sorry, thanks. Can you see my OpenSAR Lab screen now? Open Science Lab
Yes.
screen? Okay, so let me do this one more time. So you go to your home folder up here, and then you should see a folder called Conda environments. Do you all see that? Maybe this faux pas made sure you're all awake and paying attention. If you give me a thumbs up that you found this folder. If you did, then I encourage you to double click and move into that folder. Okay, so there is this Create Conda Environments notebook, and we'll go to that here in a sec. One nice thing about your OpenSAR Lab deployment is that it doesn't only come with the Earthscope InSAR kernel, but we actually have descriptions for a number of other Conda environments that you can build. And these descriptions are contained in these subfolders. There's one that's called environment configs. You don't actually have to follow along for this part, but I'm going to show you real quick, if I go into that folder, that there are a number of kernel descriptions that are available, or kernels that you can build. And the one that we'll be building today real quick is the AutoRift kernel, or the AutoRift Conda environment. And so the description for that environment is contained within this YAML file, which is a simple text file. So you can open that by just double clicking it. And it shows you the kinds of Python libraries and code bases that we will need for the notebook we'll be running. And one of the things that we're installing is Autorift, which is that feature tracking code using cross correlation. So there are a number of these kernels available. You can check them out. You can build them, and I'm going to show you real quick how to build this kernel. Okay, now we are back to following along. So please identify and open this notebook called Create OSL Conda Environments, and give me a thumbs up when you're there. So let's get you all to interact with me. I see some thumbs up. Great. So this notebook is an easy one. It runs just in a base kernel. And this is a notebook you can use if you don't know how to build an environment from command line, which you could also do. This notebook is a really handy way of doing it. So if you walk slowly through this notebook, so we run these code cells in the beginning. The first one again loads the libraries. The next code cell shows you which environments you currently have built. So you should see two environments currently, the Earthscope InSAR and the base environment. So those already exist for you. I already built the Autorift kernel, but we'll go through building the Autorift kernel in a sec. The next code cell then just sets up some paths. And then the next one allows you to, has this sort of list of radio buttons pop up. And so it has three options: use a locked environment, use an unlocked environment that comes with the deployment, or use another YAML. So if you build your own kernel, you could click on this radio button down here and then pick your own kernel to build with this notebook. In our case, we will keep this as the used locked OSL supplied environments radio button. Okay, so make sure that this radio button is selected and then hop to the next cell. So click into the next code cell. And so then run that next code cell. And again, hoping for a thumbs up, you should see now a list of environments that you can build. And one of those is the Autorift kernel. So please then click on Autorift, make sure the radio button is on Autorift, and then take your mouse pointer, go to the next cell and click into it. Okay, so make sure that once you do that, the Autorift button is selected. Then you run the next code cell, and it's going to confirm to you one more time that you did the right thing. It should be spitting out environment location will be blah, 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 / Autorift. And so please make sure that that's what it says. Excellent. And the rest of it is easy. So the next few code cells, you can just run through those. It then clears the old kernel and then rebuilds the kernel. So in my case, I already had the kernel available and I'm rebuilding it. You are building it for the first time. And so what it now does is it fetches all the code it needs in order to build the environment, and then it's going to compile the environment. So you get a bunch of verbose output here. It may take maybe a minute or so, or maybe a couple of minutes to build the kernel. And so that's a really handy way if you're not super familiar with, like, how do you build your environments, how to rebuild environments or build new environments that are provided to you. So this is now running. By the way, just a reminder, you see that it's doing stuff in two ways. One of them is next to that code cell, these square brackets, they show a little asterisk in it. So that means the kernel is currently busy, it's working. The other way how you can identify that is in the top right of your notebook, you see this little circle here. And so if that circle is filled black, then it's working. In my case, it's filled half black because I ran two code cells in a row. One of those cells has completed and the other cell is working right now. So it's done half the work in terms of number of code cells to execute. And if you hover over it, you see that the kernel status is busy. So it's working on stuff right now. So in my case, it's fetched all the stuff it needs. So there's lots of verbose outputs that you can see. It loads and downloads some more data, more information. You can see these progress bars grow. And it's currently executing the compiling of that kernel.
Will this code also works for our own machine?
Yeah, so if you take the Git repository and you clone the entire repository to your local machine, you should be able to use that notebook on your local machine to build a kernel. Yes. So my kernel completed. If you guys give me a thumbs up, if once you achieve that too. Dum 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 dum. You have a few that are ready. Maybe I'll wait. Well, I'm going to hop over to the other notebook, but I'm going to take it slow to make sure that everybody is ready to go. Okay, so now we built the kernel and now we are ready to execute our notebook. So what we do now is you go back to your main folder and we go into the 2025 ISCE Plus folder, because now we are looking at actual content. And we are today in section 4.2. So go to section 4.2. And you see, first of all, that the PDF of the slides that I showed are in here. So you can download those to your local machine. You can just click it and right click and go to download. And then there's also this notebook here that will be running next. So please all open the notebook. If you are lucky, once you open the notebook, it should already default to the AutoRift kernel. Do we have people here that, with a thumbs up, that do not have the AutoRift kernel selected at this stage? Yep, there's some of you. So if it doesn't show AutoRift at this stage, please click on that little name. You should get a drop-down menu, and you should be able to then pick the AutoRift Conda environment. And then select that. Do we have anybody that doesn't see the AutoRift kernel?
Yes, I can see it.
You can't see it. You've built it successfully, but you can't see it.
Yes, that's right.
Okay. So that sometimes happens. It takes Jupyter Hub sometimes a little bit to catch up with the available Conda environments. So the first thing you can do, the first thing we'll be trying, is just basically refresh your browser window. So you click on the little refresh thingy and reload your browser. Let's try that first. So it should reopen the notebook. And then you can give this a shot again. You can click on the little drop-down menu and see if you see the kernel now. And let me know if that fixed it for you.
No, it's still not there.
If it's still not there, the other approach is to briefly go and shut down your server and restart the server. So for the folks that don't see the kernel yet, please click on that little shut down server thing, stop your server and restart the server. And so for the folks that have this problem, restart the server. I'm going to briefly explain the content of the notebook. Once your server is back up, please let me know if you are ready to go and if things have sorted themselves out. And I see there's a question in chat. I can see it and select it, but it will not change the kernel. That one I don't know exactly what to do with. There's two ways, by the way, to how you can change kernels. You can click on the kernel here in the corner and select it. There's another way in the menu. In the main menu of your notebook server, there is a kernel submenu, and you can also use that one to change kernel. And that's another option how you can try to switch your kernel. Okay, let's give it just a couple of minutes while I explain the notebook, and then people that are restarting, please either put in Q&A or just speak up if the issue resolved.
After restarting, it's pop up now.
Oh, it popped up now. Okay. Let's see. Maybe thumbs up for folks that are not ready to go. That are not ready to go. We have a couple, and it's because you can't find the kernel quite yet. I think I'm gonna go forward out of question of time. You can, once you're ready, just run these code cells in a row. It's not a very long notebook, so it should be easy for you to catch up. Okay, so we now use glacier velocity mapping using template matching, and we specifically use this auto-rift capability. There is also capability directly within ISCE that you actually executed already earlier this week in Eric Fielding's session. And so there was a component that estimated dense offsets. And so the dense offset approach is another way how you can estimate velocities using template matching. Because that was already covered by Eric, I'm not going to redo this time. There is, however, if you're really interested in that particular approach, we have a recording from last year's course where Brian Reel gave this presentation, and he went in more detail over one more time over the dense offset mapping piece. Gareth, is that something that I think we currently don't have that as supplemental, but we could add that to supplemental.
We could, yes.
So if you're really curious about that, he did both auto-rift and dense offset mapping. So you can either look at earlier the lecture by Eric, or you can go back to the supplemental and look at what Brian Reel showed last time. Okay. So we'll go through here. Standard thing, we'll build, we pull all of the different libraries. We first actually check that you're in the right kernel. So once the auto-rift kernel is selected and you run those 2 cells, you shouldn't get an error message. Oh, there's a lot of stuff in the chat. Anything I need to talk about? Off-topic question.
This is listed as homework on the in Moodle and on the syllabus, and you have a big sign saying this is not a homework.
Oh, well, the big sign is wrong. Yeah, so in the end, you just have to submit the notebook. So it's not a big extra effort. So we load now the Python libraries that we have available for this kernel. We will be creating a little folder that's called /data here. This is where sort of the input data will go in that we use for offset mapping. And then we define a little function that will help us handle all the GDAL content, all the coordinate content in the data sets that we'll be working with. And so we will be using basic cross-correlation based template mapping in our approach. And so auto-rift, in the end, as it says here, is a template matching Python library that's open source. It was developed by the ITSLife project and is in operational use by the ITSLife project for global velocity mapping. It measures offsets, based on users specified grid spacings. So there's a set of parameters that we can set. We will look at those parameters a little bit. Those are the ones that we already talked about in the lecture. We can select the chip size. So that's the size of the template we want to use for matching. We can select a search space, which basically converts to the maximum velocity that we want to allow for our template matching. We can select that and a few additional parameters. The way cross-correlation then works also in auto-rift is we have a template. That's that red thing that we basically move over a scene. For each position, we calculate a cross-correlation coefficient between the template and the background scene. And then if the template is in its right place, so if the red box is over the blue box, we hope that this cross-correlation reaches its maximum. And this way we can identify that template in the scene and measure its offset relative to the original scene. How cross-correlation works, I have a little one-dimensional example that I want to show for template matching. So I have a little script here that calculates two data sets that are offset from each other. So that could be anything. This could be a cut through a SAR scene, for instance. Maybe in this case, one where there's a lot of variation of radar brightness. And so I'm taking the reference data set is the blue line, and then I'm offsetting that data set by a fraction of a few pixels. I think it's 5 point something pixels. Can't remember exactly, 5.5 pixels. So I shift the data sets relative to each other, and then we try to use cross correlation to then estimate that offset that I just created. So those are the two data sets. That could be a realistic one-dimensional cut through a SAR scene. And so now we use cross correlation. In this case, we use a SciPy implementation of cross correlation to calculate the one-dimensional offsets between those two scenes. So this is what that next patch is doing. And so this is what the cross correlation output would look like. So what we did now is we moved that template scene, the reference scene, over the shifted scene. We calculate for every movement step a cross correlation coefficient. You see that for most positions of that template, there is not a large similarity between the template and the underlying scene. But when those two data sets are perfectly aligned, we get this very large spike in cross correlation, where the cross correlation in this case actually rises all the way to 1 because the data sets are identical. So I just shifted them, I didn't modify them. And at the perfect offset between them, we get a cross correlation value of 1. And if you look very carefully, that cross correlation peak doesn't show up exactly at position 0 because I offset the two. So ideally, this peak should show up at 5.5 pixels offset. So we can then look at what offset actually estimate we get. And so here my estimated offset estimate is 5.59 pixels. So we are pretty close to the offset that I artificially created. So question. Oh, okay. So then, of course, in reality, the two scenes that we are comparing, they're not identical. There's some differences between them, which will impact how well cross-correlation can work. In this case, what I'm doing is I'm just adding noise to the data set. So I make those two data sets not perfectly the same anymore. And so I add noise with a certain signal-to-noise ratio. In the first example, the noise is fairly small. My cross-correlation still looks really good, and my shift estimate is still very close. Then I lower that signal-to-noise ratio, which is equivalent to saying I just add more noise. And you see now that the peak relative to the background noise is getting a little bit lower. My shift estimate starts to get a little bit wonky, not as accurate anymore. And so the more noise I add, you can see more and more how that quality of the match is degrading. And here, when I add a ton of noise, you can see that it's very difficult now to actually identify that correlation peak. This is to basically demonstrate that in some ways we expect that the two scenes we compare are actually comparable and contain similar content, so that I can actually identify that content in the scene. Let's see what there's a question. Yes, so there are NaN values and zeros can cause issues. So we mask out all of the image contents that we don't want to use for matching that may distract matching. This is NaNs, these are zeros. If you have optical scenes, you may also want to mask out clouds, for instance, to not distract your template matching approach too much. So this is what's going on conceptually in AutoRift. Of course, AutoRift contains a lot of sophistication. to first pre-process the data set. So it does gradient calculation instead of using the images themselves. And it does a lot of work in filtering the outputs. So it uses neighborhood information to assuming that the motion we estimate doesn't randomly change from one pixel to the next. It allows you to include limits for how large of an offset you would allow, it uses actually for AutoRift that's operationally running. It uses a lot of information about the glaciers themselves, flow direction and flow velocity to make the velocity estimation robust. And so in the end, AutoRift, this is basically taken from my slide deck. It does this template matching approach. It takes any kind of NumPy array as input. So as long as you have a stack of NumPy arrays as inputs that are geographically aligned, so we're assuming that there aren't any large background offsets between the scenes, you can run those NumPy arrays through the AutoRift workflow and measure offsets between them. So this should make this notebook reasonably adaptable to different kinds of inputs. Right, and so the AutoRift, my notebook behaves kind of strange. When I scroll down, let me see if I can click into that cell somehow. So there are certain AutoRift parameters that you can set. So this is something you can play around with in your own time. So one of them is the template patch size. So that can define the quality of your matches. If you have a scene that has a lot of contrast in it, it is fine to keep these templates very small, because then even a small template will capture enough radiometric variability so that you can match it robustly against background. If the content is reasonably smooth, then you may want a larger patch size. And another thing that AutoRift does, it can vary the patch size a little bit based on image content internally, but you give it sort of a starting patch size. You can select a step size. So these are the size of the offsets between template image patches that you can define to speed up processing. You can set the search distance, so that allows you to cap the maximum velocity that you want to search for. That can also help you with filtering bad matches. And you can provide a number for oversampling. So if you want to get to the sub-pixel accuracy, it is recommended to oversample the data set first. And so you can decide whether you want to do oversampling and how much oversampling you want to do. And so this figure shows you how AutoRift works. AutoRift, by the way, stands for Autonomous Repeat Image Feature Tracking. I don't know if that's one of these cases where the acronym was first and the full name was second. I can't attest to that. And so it uses normalized cross correlation. And it uses sort of a nested grid design, which is shown in B, where you sort of the scene is tiled into these grids, and those grids are searched separately. The grid is defined in geographic space, not in the image space. And so it allows for oversampling to be better with estimating the actual offsets. It's demonstrated a little bit here, where on the left patch would be if you do offset matching using the original resolution image scene. You're kind of limited to finding the offsets at the pixel size, sort of in integer steps. If you want to do sub-pixel estimation, oversampling the data set can help, and the same cross-correlation function looks then much more easily interpretable in the oversampled case, and you have a much better time finding the peak offsets between the two scenes. Okay, so we'll be running through AutoRift first using a pair of actually optical scenes So we use a set of 2 Sentinel-1 scenes over Malaspina Glacier. This is the glacier that I showed you earlier. Because AutoRift is sensor agnostic, conceptually, you can feed whatever sensor you want into this data, into this framework. And so we're using an optical pair first to give you an idea, and then later I show you a SAR time series. And so we have a pair of Sentinel-2 images over Malaspina Glacier. They were acquired in May 2020 with an offset of a few days. I think it shows you exactly how many days here. So we have 15 days offset between those two. For optical images over this area, it actually gets a bit tricky. It's a fairly cloudy region, but it turned out that those 2 scenes in May 2020 were cloud-free. You could find these data sets on NASA or other resources yourself, but in this case, I parked these data sets in Amazon in Amazon S3 for you. So this code cell just fetches these data and pulls them down. And so Malaspina is a large Piedmont glacier in the Alaska Panhandle, so it's sort of in southeastern Alaska. It's a beautiful glacier. If you look at it, it has this very large fan in the front of it and sort of moves out of the interior like this. Malaspina is interesting. It has very strong seasonal motion, like most glaciers in Alaska, where sort of in the summer, the movement is higher because there's more water input. In the winter, the movement slows down. But it also is a surging glacier. So it has phases where it surges, where the velocities go way up for a period of time. And so we'll look actually at the end phase of a surge here in a sec. So we now start preparing for AutoRift. So this prep AutoRift function allows you to prepare your AutoRift approach. It inputs the primary and secondary scene that you want to compare, and then it allows you to set variables for those search parameters that you would use. So there are defaults for those variables. So the step size is usually 16 pixels. The minimum patch size that you start with is 32 pixels. The maximum is 128. So between those two values, AutoRift is going to try to find the optimal patch size for every region. For a reasonably featureless region, it would opt for something closer to the maximum patch size. For a reasonably gradient-heavy region, you would use a smaller patch size. You can set minimum and maximum search distance. Maximum makes sense. It's set to 10 pixels. You can use that to then calculate what the maximum velocity is. You can interpret here. Minimum search space you could also vary. For instance, you may not be interested in points that haven't moved. So you could set that minimum search distance to something other than 0, for instance, to not accept 0 offset pairs. So, run that script. Then we tell it what the 2 scenes is that we are looking for. So those are those 2 Sentinel-2 scenes that we are comparing here. The next code cell just visualizes them to just give you an idea of what they look like. This can be useful to make sure that you're not running, if for optical scenes you don't have heavy cloud cover. There could also be cases where there's significant melt happening on this glacier between 2 scenes, which may make feature tracking between them not very useful, as you can also look for things like that. So those are the 2 data sets to be looking at. This is optical, so that's kind of tricky because there are many areas that are reasonably featureless. And so especially in this fan out here, AutoRift is going to run into some issues, as you will see, because there's not a lot of features on the ground. And then we actually run AutoRift. And so AutoRift is optimized for throughput because they want to do global processing. So you will see that this cross-correlation approach runs actually fairly quick. So we run this prep AutoRift function that we've looked at earlier. The only thing I set here is the step size. That's something that you can play with. I set it for 16 pixels now, but you can change that later on if you want to and see how the quality of the matching result may change. There are a few warnings that are being popped out. That is often the case. In this case, if we have patches where we have where masked out pixels, you get these warnings. So don't worry about those warnings. And next, we can then just visualize what we just produced. So in this really short time, we got we measured offsets for all of the patches that we've analyzed, and we get this two-dimensional offset map. There's lots of questions. Anything?
Yeah, I was saving them up for you for a good moment. I guess this is a good moment.
Well, that could be a good moment. So what we have here, how do the auto rift is affected by geometric distortions? Yeah, so we are for SAR actually what auto rift uses are RTCs, so they are corrected for geometric distortions, so that it's easier for cross correlation to be a valid approach. Geometric distortions as such are fine as long as they are the same in both scenes, so that offsets that you want to look at are actually only related to ground motion and not to geometric differences. So that's the first. You want the offsets that you're measuring to be related to motion and not necessarily related to different geometries. The other reason is if there are strong geometric distortions that are different between the two scenes, then cross-correlation theoretically is not a good approach anymore, because it assumes that the two scenes are only different in terms of translation, absolute radiometry, and potentially noise floor. But if you have non-linear, non-affine transformation between the two scenes, then cross-correlation is not really an applicable approach anymore. Can we limit the SNR for pixels? So what you can do is when you look at the match quality, so if I scroll up real quick for this sort of 1D example that I showed you, you could say, you could calculate a metric that's something like a peak to side lobe ratio-ish, or sort of a correlation peak intensity versus sort of background noise. And you could threshold that. And you say, like, I don't accept matches where the difference between the peak power and sort of the background power is lower than a certain number. So that's certainly things that you can do to clean up matches. Which is, what is the minimum displacement that can reliably be tracked? So depending on how much oversampling you do, you should be able to track down to a fraction of a pixel. Maybe realistically in a 10-fold oversampling, maybe an eighth of a pixel. So if you know your pixel size, you can then, back of the envelope calculate what the minimum displacement is that you can measure. And it's certainly not as good as InSAR. That's why many people, they use InSAR for like the interior of Greenland, where the motions are small enough for InSAR. It gives you the more accurate measurement. And then in the outlet glaciers where the motion is very large, they switch to offset tracking instead. Which values indicate eastward and westward movement in the east-west plot? Yep. So actually, I'm take the eastward direction. So west to east. So west to east is positive, and east to west is negative. Let's see, does that make sense? Or is it the other way around? West to east. Oh, yes. So positive. So the blue is west to east. So this glacier moved from the west to the east, and then red is east to west. And so you see that in Malaspina, here in the middle, it actually switches signs as it sort of bends around this corner, and has sort of a small section where the motion is predominantly westward, or is westward, and other places where the motion is then eastward. Maybe I'm gonna go quickly through the rest of it and then answer these questions afterwards to not fall behind too much. So what you see in these, so one reason why I don't usually like removing zero offset matches, or very small offset matches, you could set up AutoRIF to not give you this sort of blue background, it's really useful to understand two things. One of them is to verify that your two scenes didn't have some sort of an overall offset relative to each other. So you would expect that in places where nothing's moving, that you should also estimate zero motion. So that's one way why it's worth keeping those estimates. And then, as we had discussed earlier, we often may want to know what is the noise floor or the accuracy of the estimates we get. And so one approach how you can do that is you could look at the offset estimates in places where you don't expect any motion, similar to what you would do for an INSAR case. So that's two reasons why I like keeping those data points, because it allows you to do some error analysis, and it makes sure that you are not distracted by some sort of background offset. Other thing you see here is I looked at, so down here, this is this large lobe that Malaspina is creating, and that one is fairly featureless. And you can see issues here where you have poorer matches in this area because of this low feature richness in that space. So this is this data set. You could now take the north-south and the east-west component and convert them into sort of a two-dimensional vector field, velocity vector field, to analyze this glacier. And you could imagine that you could now use many, many such pairs to get a full time series of motion along Malaspina. To do this, I'm actually not going to do this directly in a notebook. Will be to do a time series analysis will utilize an implementation of AutoRift that is actually publicly available to you. And I'm going to how much time do I have left, Gareth?
None.
None. So then I'm not going to demonstrate this to you, but ASF, through its search interface, Vertex, I'm not sure if you see that pop up, there is actually an ability for you to create AutoRift image pairs from Sentinel-1 scenes. And so what I did in this last exercise is I went through these steps. I went through the ASF search interface. I went through these steps to select pairs of Sentinel-1 scenes that I wanted to use AutoRift on. And then I did custom processing and did AutoRift offset creation for Malaspina from Sentinel-1. And so also that data stack I deposited on S3. So this code cell pulls this data set and unzips it. And then we stack it up. So we take all of the image scenes, we make sure that they're stacked up. We extract the image acquisition dates. This down here then shows you what the image acquisition dates are. So I created 70 image pairs with their relative acquisition dates. I was lazy here and I just picked the first of the two scenes. So because AutoRift compares two scenes to each other, each AutoRift result actually has two dates associated with them. And the right approach would be to take both dates and then maybe use the middle of these two dates as the representative date for this particular pair. I was lazy and I just took the first one, sort of the first scene as my reference date. And there was a question earlier about masking. So I'm masking out some bad matches here for visualization. And then what I'm doing here is I calculate the mean velocity. So I just take all my velocity estimates and calculate the mean of it. And then I can visualize that. So you get a plot of that mean velocity calculated from these SAR scenes. We still have issues down here in this low feature area. What I also did here is I have a little script that I built that's called Pixel Picker. And what it allows you to do now is you can go to this map and you can click on one of those pixels. So here I'm clicking on some of the fastest parts of Malaspina. And then the next code cell is then extracting these pixel coordinates. And then I can plot the time series of velocity at this particular pixel. So here you see that this is a very fast flowing part of the glacier. You see that in sort of the warmer periods, the velocity has gone up. This is actually at the very end of the search period of Malaspina. So 2021 was sort of the last year where it was really fast. It then slowed down, partly because of the end of the search, and then partly because of the colder season. And then you can see that in 2022, the ice velocity at this same point was substantially lower because the search at this glacier has ended. So I encourage you in your off time to play around. So for the submission, just click on some interesting points and extract some velocities that you might find interesting. So this is a different part. Here the velocities are much smaller, so it doesn't quite look as nice. What I'm doing here also is I actually average auto-rift outputs in a 5x5 neighborhood. So you could also change that. You could make that neighborhood smaller if you look at a very narrow glacier and experiment with those parameters. You can also, if you want, go back to the earlier example for Landsat, and in the auto-rift call here, where is my auto-rift call? Oh, it's coming down here. So where you actually then run auto-rift, you can change these several of the parameters. You can set this to a different step size. You can change the maximum or minimum velocities that you allow for, and so on. So you can make some changes here and see how this changes your output quality of the velocity estimates that you're achieving here for Malaspina Glacier. So feel free to play around. You can also, if you are curious, you can follow these steps here to order your own little data stack over another glacier. I would stick to glaciers using ASFs. You can go to ASF, follow these steps, and create the own little data stack that you can then run through auto-rift to do velocity estimation. And I will stop at that and see there's some more questions. When defining reference scene, where are these two values coming from? That's a good question. I'll get back to you on that. Camilo, I have to look back in the code. I can do that during the break. What is the minimum velocity that can be accurately measured? I think we addressed that already, didn't we?
Maximum, yeah. You said 1/8 of a pixel.
Yeah, depending on what your oversampling is. And you know, it's going to vary a little bit through the scene. If you have a low contrast patch, the cross correlation peak is not as narrow, and that sort of makes your estimate a little bit worse. So you can't necessarily always say that for sure. In the end, what I would do is I would use non-deforming areas and analyze offsets there to get a better sense of what the noise floor is. Oh, you have some errors with widgets. You may have not run a code cell. It says like displaying widget not found, the cell after pixel clicker. You may not have, are you sure you ran this code cell that actually defines the pixel clicker function? So you could make sure that you didn't miss a code cell. That could be a problem.
No, I ran that one and it worked. And the next one, it came back with model not found.
Oh, okay. So it didn't the matplotlib widget. That's odd. Yeah, you can post on Slack, and I can see if I can help get maybe Alex's help to debug that with you. It should be part of the kernel, so it should have worked. Seems like worked for most, but we'll figure it out. And then what's the other one? Oh, okay. Yeah, so play around with this particular notebook if you can. I encourage you to also create potentially your own stack at some point. I can't remember how to get out of sharing. I can see my, here it is.
We're
And
very
so
far behind schedule.
Yeah, and in the slide deck, there on the very last slide, there's a link to the AutoRift website where you can explore AutoRift outputs for various glaciers around the globe. So feel free to look through that too.
Okay, I propose a break for maybe 5 minutes. I see Rowena is here and waiting patiently. Are you good
You
for?
know, it's a change of gears, and it's probably doesn't need the whole time period anyway. So I think it'll be fine. If we take a little break now, I can still try to get us back on track for the ISCE 3.
Super.
I'll
We're
just
all here
talk
for
really
that.
fast.
You would never do that. All right. I see Melissa's already started a countdown timer, so we can take a brief break.
And I think we should collectively apologize to Ravina, because that's like the third year in a row where you ended
Yeah,
up in space where we sort of are delayed.
it's okay.
Come on.
I've done
Or
it to
it's
others, and everyone we all like hearing you talk, so it doesn't
oh
matter.
sure. See you in a bit.
Recording is resumed. Rowena Lohman is here. I think this is your first appearance on the in the live sessions.
Yeah.
She's going to tell us about the acquisition geometry and how you can decompose velocities. And the floor is yours.
Thank you. And just for a quick intro, my name is Rowena Lohman. I'm at Cornell University. I used to work mostly in earthquake science, and now I do kind of other things with SAR, including looking at soil moisture and other types of things that affect ground deformation. And let me share. I'm just going to share my whole desktop. Boy. Oh no. Sorry, I'm having the whole system settings issue. Give me one
System
second.
settings, like, okay.
Yeah. Should be okay. What?
Oh, should be back in a minute. I guess. Be waiting for that reappearance.
Yeah, sometimes the computers want you to do the
She's coming back.
or approve that it can be used kind of thing. So there we go.
There we go. That looks better. Okay, I'll share this desktop. Sorry about that. They keep changing up my versions of Zoom that we have here at Cornell. Can you all see the screen that says decomposing InSAR velocities?
Yes.
Great. And so, yeah, what we're going to talk about today is a couple notebooks that Gareth put together a few years ago. So it's always funny for me to present these in front of the person who actually wrote them.
I can
But hopefully
hide.
you won't. What?
I can go away.
No, you do whatever you'd like. And so what this is really, it's a bit of a change from the other things we're talking about this afternoon, which are really about ways you can process the data. This is more about interpretation. And so as you've seen in the previous lectures, there are, excuse me. With InSAR, we're really just measuring things that are between the satellite and the ground, right? This is kind of what's talked about in this first text chunk up here. Now, there are often cases where people want to know how much the ground is moving up or down, or east or west, rather than just it's moving towards or away from the satellite. This is particularly important if you're trying to compare results from maybe ascending and descending data. You can't make interferograms between the two, but you can have, or overlapping tracks, things like that. And so when we do the sort of manipulations that are done in this notebook, you get at least a model of how much the ground might be moving in a vertical direction versus horizontal. And so I'm going to just go through this notebook. I had the question window open, now I don't. Let me try to find that. Yeah, now I can see it, just in case there are any questions that come up. All right, so set of data that is used in this first notebook is a really nice one from Berkeley in California, where there's a series of landslides in the Bay Area. And the data itself is shown in these two images. So you have this one image, which is from a descending interferogram, or a set of interferograms, where they have actually used quite a few Q&A. Okay. You can't see the kernel. Oh, okay. Well, quick answer, just I am doing this on my desktop so that I was not competing with all of you for OSL space in the cloud, right? This is actually a very small self-contained notebook. So I just copied it over to my desktop. That's why the kernel I'm using is different from the kernel that you would use. But the only thing that's used in this particular notebook is NumPy. So you can basically any of the kernels should work. The other one does use MinPy. Hopefully that answers the question. All right, so what's shown here are, it's a little different than some of the interferograms we looked at before. These are individual pixels that had very kind of robust characteristics in terms of their scattering behavior over time. And what you can see here is the direction of the satellite. So in this case, the satellite is traveling in the direction marked by the T arrow, and it's looking in the direction shown by the L. Okay, so this is descending, moving towards the south, north is up in this image, and it's looking towards the right. And then the color here is showing motion towards or away from the satellite, and kind of these polygons here are some of the known landslides in Berkeley. And so you can see that there's a difference in rate, and the average rate within each of these polygons is shown with the numbers here. These are numbers you'll see lower down in one of the cells where this data is used. The other information in here that you're going to need to actually make this notebook work is shown here. This is showing basically the direction of the satellite. Here, this is the 191. That's the degrees from north that this satellite is traveling at, and then the look angle, which here is 23 degrees. So you'll be inputting those two numbers below. So this is the 1992 to 2000 velocities in the descending direction over this area. If you look a little further down, you could see the same location, a slightly different time span. And this is now a different satellite, and this is now ascending data. So in this panel below here, the satellite is moving towards the north, but again, still looking towards the right in the direction of the L vector. So now these same polygons are shown here with the rates within them. But now again, we're observing from a different direction. And so the sign of these landslides relative to the surroundings is different, all of that. If you go back up to the first one, another nice thing I just want to draw your eye to is that even outside the landslides, there's something very interesting here. This kind of bluer color and the turquoise color, you can see they're kind of separated here. And this is one of the faults within the area. Okay, so that's the data that we're looking at in this area, in this notebook. And so again, note that there's differences between the sign and the magnitude of what's going on in the landslides and their surroundings within each of these. So now we go back and look at what we're going to actually be doing. So just as you saw in some of the, I'm just going to be probably reviewing things you've already had, but just this mostly to give you an idea of the geometry here. This is if we're kind of looking, excuse me, along the direction that the satellite is traveling, the ground surface would be here in green. The kind of orange vector is the direction the satellite is looking. And these angles here are basically defining how this look direction fits in three-dimensional space. So here again, we're just looking at one cross section. The next figure is looking from above. All right, so if we have this angle of incidence of the radar to the ground, then the vertical component of this vector, which is here or this side here, is just the cosine of that angle. And similarly, the horizontal component is the sine, right? So relatively simple breakdown there. When we're looking from above, now the important angle is the one that kind of shows the azimuth or the heading of the satellite. That's the one that was shown up above there too. Now we just have to basically think about how the proportion of the horizontal that we got up here is divided up between east and north, right? And all of those equations are shown here. I'm not going to go through that too much just since we are a little limited in time, but you can see again that the angles we had above and this azimuth angle both come into these equations. So if we put all of that together, we get these three components of the look vector, which all are related to cosines and sines of the azimuth and the look angle itself, right? So the next bit of the code just goes through and basically calculate, when you get that, this will be blank. So you will need to go and paste in the numbers from the image above. So here we have that the incidence angle for the ascending image and the azimuth angle for the ascending image that's above. And then we have the, excuse me, this vector here that was shown in the text is just exactly the same math right here. Okay? So when we run all of these, you'll get a vector that looks something like this. So now the way to read these is we're looking at the X or east-west component, the north or north-south component, and then the vertical component here. We can do the same thing below for the descending. And again, we get different numbers. This is the east-west component, north-south, and vertical. So something to notice right away is that the vertical component in each case is negative. And so this kind of makes sense, right? If the ground is moving up, if that's our convention, then that will make the line of sight shorter and will make that get smaller. In both of these cases, the north portion, the y component for this vector, is relatively small compared to the others. And the x component is a little bit bigger, but still smaller than the vertical, right? And the sign of the x component, the east-west one, is different. And this is really what allows us to at least to some degree, decompose the look angle data into, say, east-west or vertical, is because the sign we expect for the east-west differs between the ascending and descending tracks. So we're going to go through the example for the landslide case, but you should see right here that if both the ascending and descending data have the same sign, that tells you that the motion you're seeing is most likely, if you had to guess, would be vertical. If they have different, if the ascending and descending have different sign, that's kind of a hint to you that it is probably mostly in the horizontal component. And so the next step is to basically put all this in matrix form so that you can take a vector of observations. It could be just one combination of ascending and descending at a single point. It could be for the whole set of landslides that you have, or it could be for an entire image, right? Where you have ascending and descending values at every single pixel in your image. And so the way it's done here is they basically make a vector of the horizontal and vertical velocities you eventually want. So this has to have the same number of pixels you're analyzing. And the the matrix of kind of look angle information that we just looked at before is how you relate this true velocity field that you're looking for with, say, horizontal and vertical, east-west in this case, and up-down, to the line of sight values that you actually have, right? So this is sometimes called the forward part of an inverse problem. And so this matrix P is just those values we looked at before, except that we're kind of in a way not using one of them right now. We're ignoring the north value. We're just looking at basically the east-west horizontal and the vertical. And so we calculate these based just on our knowledge of the look angle and the azimuth, and we get this 2x2 matrix. Right, so then you put all of these things down below, and as Gareth said, this is basically, we're forming what's known as the least squares solution for a given vector M. And so if we have this matrix P we just made and it operates on the true values, we should get the vector of line of sight values, right? So this is what in a way would generate the data we actually have today. And so if you go through these steps and you instead kind of reverse that, you get the inverse problem, then we can say that the model, the vector M that we want, which is the horizontal and vertical models, is this combination of the matrix P times our vector of data, which is the line of sight values, right? And so if we do that, this is basically just, again, taking the ascending values that we calculated before for the look for the look vector and the descending and putting them into a matrix. So it's just making that matrix P. It looks like this. You can go up and see it's the same values we had before. Here are the two horizontal vectors, and here's the two vertical ones for ascending and descending. So then when you run through this, all that's in this central part here is the values from above that were kind of written next to each of those polygons for the landslides. You can go and compare. It's exactly the same numbers. And this is that this is that operator up here. It's P prime, P inverse times P prime. That's just formed right here. And now you can just loop over all of those different values for the landslides, and you'll get out a velocity for each one, right? And so that's what happens here. It's telling you a little bit about how much at each point, how much it's moving east or west, and how much it's moving up or down, okay? And I was going to go through it. One of the things I was going to play with was, what if you just make yourself some fake data where both line of sights are 1, both line of sights are -1, one of them's 1, one of them's -1. If you do the exact same thing and put that in here for R, instead of R, you'll hopefully be able to see that it divides itself up into horizontal or vertical in the way you should expect. All right, we are running out of time, but there are a whole bunch of citations here. So I did want to at least touch on the MintPy one, just since it's a little more complicated. So in here, am I on the right? I think I'm in the right kernel. Yeah. I'll just get started. So this one, again, it does rely on MintPy and OSGeo, so hopefully those are all working for you. This is just a function that Gareth put together. And so what this project does is, again, it's reading a pre-made data set for you. It's basically 2 fields of the the different line of sights for a given area. Okay, I will. Yeah, I don't think I have time to go through that, but I'm just looking at the question. Okay, so if I'm going to just run this. So the data is all here. It's already stored in the area where these notebooks are held. And if you crop it, you will eventually, this will run. You should plot the data. It gives you a lot of nice things, just verifying that your latitude and longitude are sensible. And what you can see here is that the raw data we're putting into this experiment. So you have line of sight velocities in the descending direction and in the ascending direction. And hopefully the first thing that you should notice is that both of these have a big blob in the middle that has the same sign. They both have a big negative area in the central part. And as we kind of talked about before, when the sign is the same for a signal for descending, ascending, it's probably mostly a vertical signal. So you should already kind of know what the answer is going to look like when you get to this point in the notebook. In this case, they're picking a reference point. You can use a different one than what's shown here. This is kind of related to some of the MintPy stuff. And let me just go through what the next thing is here. Since I think I'm going to take a whole 5 minutes left, and then we'll finish in time for break. And plot what you get at the end. And you get kind of exactly what we should expect. There's a huge blob in the middle that's vertical velocity. This is an active area of geothermal power production. And there's east-west velocity, basically material moving this way and this way. So you kind of radially outwards from this central source, okay? And the last cell, which I'm not going to run, basically prints these to geotiffs, which is kind of a nice thing to have. What I did want to show was that the big difference from what we did before and what this is doing is that it's not just doing it at a single point. It's doing where we have fixed one line of sight, one azimuth. We've actually have a whole grid of line of sight and azimuths in this case. And we can see that just by looking at, oh gosh, what is it called? It is the incidence angle. So if I just instead plot the value that it uses when it makes that matrix of the look vector, you can see that in this case, we have a whole kind of range of incidence values because that's what the real data has, rather than just a single point. Okay? The azimuth values don't look quite as, they change a little bit too, I think. A little bit, oh, I don't have the color bar up here, but there's not as much of a difference. Okay. And I've gotten us to the 3:51. We were supposed to have a break, so I was to try to stop before that need for a break. So maybe I'll stop now and see if people have questions. I don't believe there's a actual homework related to this, right, Gareth?
No.
Yeah, so this is
No, there
more
isn't.
for just, yeah.
All your information.
Yeah.
Well, thanks for that. And thanks for the heroic efforts to get us back on time. I'm not sure it was your responsibility to do that, but.
Well, I know I have to leave at 4 anyway, so I couldn't go over.
Okay. We'll give you the first time slot next time, and you can take as long as you want.
Oh, you don't want to sell me that.
Anyway, does anyone have any questions about this? You can. This is great if you have processed lots of data over one place and you're curious to like figure out what the signals mean. In this particular case, yeah, it's a geothermal field that's contracting and subsiding.
I just got a question in the chat about the 1 sigma uncertainty. There is a slight issue with that. I don't know if we want to try to fix it, Gareth, but what the little equation that's shown in there is, it's a nice trick for if you know your design matrix. In our case, that's that thing that relates the true model to our observations. If you know it, you can basically use the equations that's shown there to estimate what the error on the model is as well. What's missing is that you should put in the error on your input data, right? So what is inherently assumed in what you see there is that the error is normal with 1 for a standard deviation in whatever units the data's in. And that's not going to be generally true. So if you take inverse methods or anything like that, at some point, the way that works is each of those like P prime P's you see in there, you kind of pull those apart and you put a data covariance matrix in there that accounts for some points being noisier than others or whatever. And if all the data has the same standard deviation, you can just put a sigma squared in there. And so you basically are propagating the error in your data through the inversion. And you can almost think of it as inverting a whole bunch of data points that just have values of 1 sigma, right? That gives you, in a sense, the expected error range on your model. Hopefully that answers your question.
Yeah,
Oh,
we're
okay.
using the formal uncertainties, not the true ones.
And none of the errors are Gaussian anyway, so it can be a useful tool. You're answering the east-west question?
Yeah, so what the interpretation is, the area in the west is moving to the east and the area in the east is moving to the west. So the 2 areas are horizontally contracting or converging on each other.
I misspoke.
So if you're removing volume from the ground, yeah, the surface might subside as you're taking material out the ground, and also the sides of on either side of that reservoir, you're sucking the crust inwards, basically. So yeah, it's consistent with volume reduction in the crust. And they are probably taking more steam out of the ground than they're replacing between kind of dry seasons. It seems to be a commonly observed feature in every geothermal field I've looked at.
And I didn't get into it because it's a little touchy, but the whole idea of north doesn't matter in any of this always kind of makes me cringe. If you look at the 2 look vectors for the Berkeley example, the north values aren't actually the same, and the time spans are different. So that assumption that we're really only sensitive to east, west, and vertical, it assumes that that basically you have the same time interval, that all of these vectors really do cancel out in ways they don't always. And so it's just something to keep in mind if you work with this sort of data, that even this east-west vertical thing is still a model, and there are other things that could be biasing you and thinking. So if there is true northward deformation, it isn't going to completely disappear when you do this.
Right. And that's why we're all looking forward to having a left-looking satellite operational soon, which will give us more information about that north component. And we might be able to do this notebook in 3 dimensions in the future, which will be fun.
Even if some of the crowd people are sad about the North Pole.
They've been having a great time with the North Pole so far, so like, give us something new to play with. Okay.
Maybe one last thing, plugging in, plug for some of your work, Rowena. Rowena published a paper with, was it with Mark Simons on sort of formal error estimation or error models for InSAR, right?
Yes, yes.
You can put that in chat for people to look at.
On the slope that. Oh, okay. That is I'm looking at the chat. This is a question about motion on a slope, line of sight. Just a note is that there are some, I don't know if this is what you're looking at, but there are interesting things people are seeing all over the world where they are seeing downslope motion in long time series. And it looks like you are seeing uphill motion. Huh.
I mean, it could be internal deformation of the landslide itself, or it could just be that the assumptions that you're making about the relative strengths of the various components, or the lack of importance of a north component are incorrect here.
Or you're seeing soil moisture or phase closure things related to vegetation that are giving you a signal with that sign that has nothing to do with ground displacement.
I mean, Rowena didn't dwell on it, but there is one example in the Berkeley Hills notebook where the vertical motion is basically slightly positive, which isn't true, but it's a function of the assumptions that we're making. It's very close to being horizontal. Yeah, one of them is going up.
Yeah.
But
number 2.
Number 2. But that's probably smaller than the error.
Okay, velocity maps for nonlinear deformation. So you how does what affect it? Do you mean like the?
I don't know if they're asking whether or not, because we're assuming a constant velocity, and obviously the velocity, the displacement might not be linear over time. It might surge and slow down. You have to, if you want to use two time series instead of 2 velocities to do this, it's a lot more complicated. You have to interpolate the 2 displacement time series onto the same time scale somehow, because they won't have the same acquisition dates. So you need to account for that and make an assumption about the consistency of the deformation. I've started to dabble with this, but it's difficult, because one of the benefits really of the velocity data set is it's very stable. You're basically averaging out all the noise that could be present in your data by assuming it all follows a trend. And to first order in this location, it does. But yes, if you have very unstable deformation with time, then it's much harder to invert it. There's a lot more stuff that could creep into the signal. I would say like my AGU talk last year, but it was an attempt to do that, and it wasn't a very clean decomposition in that case, unfortunately.
Well, I have to run, but it was very nice seeing you all.
It's great to see you. I think we'll take a 10-minute break, and when we come back, we have Jeff Gunter from JPL to talk about ISCE. Back, everyone. I see Jeff is on the call, and I hope he's ready to go. He's going to present on the new code developments that are coming down the pipe in ISCE. He's shared his slides with me, and I have uploaded them to the GitHub repository. I'll put a link in the chat that you can go and find them there, and you can download them from there. If you restart your server, eventually they will show up in the corresponding folder on OSL, but probably you want to pay attention to the presentation and not mess around with OSL. But the floor is yours, Jeff. And
Thank
welcome.
you. Thanks. Yeah, I'm happy to be here and talking about ISCE. I am not usually a user of Zoom, so you might have to bear with me. I might run into the same issue that Ruina had where I have to enable permissions. So let's see if I can get this to work. Yeah, okay, so I have to open up my settings. Enable Zoom. Okay, yeah, so I do have to quit and rejoin. Just bear with me for 1 sec.
No problem. I'll let you back in.
Everybody finding the slides okay? Super. There's this question about 3D decomposition. Whilst we wait, we need at least 4 inputs: line of sight, ascending and descending, azimuth and range. No, you only need the azimuth offsets. The range offsets are duplicating the line of sight displacement from InSAR. The range direction is still the range direction, even if you're measuring it with offsets. So yeah, there's not much to gain by including them, but you might want to include 2 azimuth offset estimates.
Only if you just don't have any coherence, I guess. But
I guess, yeah.
All right, I think I'm in. Hopefully someone will.
We're seeing your web
see
browser.
your screen. Yeah, we see your Zoom.
Oh, okay, wrong desktop. One check. Should be this one. How about now? You see the slides?
Yep. Slides. Yep.
Excellent. Okay, yeah, so thanks. So my name is Jeff. I'm one of the ISCE developers. My colleague Haresh was planning on giving this talk introducing ISCE, but he ended up being busy working with NISAR commissioning. It's a very exciting and busy time for the NISAR scene, the NISAR team. But so yeah, so I ended up being a little bit less busy, and so I'm very happy to get a chance to give an introduction to ISCE. So I'll talk a little bit about the capabilities of ISCE and kind of how it fits into the ecosystem of SAR missions and science applications and what the current status is and what our future plans are. And just feel free to interrupt me at any time if you have questions. So first of all, what is ISCE? So it stands for InSAR Scientific Computing Environment Enhanced Edition. I think this is supposed to be a little tongue-in-cheek. It started out as just ICE version 3 as a follow-on to ICE 2. And I think somebody had the great idea to call it Enhanced Edition. It's an open source library for SAR processing and for analysis of downstream SAR products, very similar to ICE 2. And has a ton of capabilities. We use it for everything from image formation to calibration to geocoding to interferometry and phase unwrapping and more. It's primarily a Python library, so the API is in Python, most of the usage is in Python, but a lot of the backend code is actually written in C++ for performance, and we have some CUDA code to leverage GPUs as well for some of the processing. I think at this point, you're all at least somewhat familiar with ICE 2. So a reasonable question might be, why ICE 3? Why not continue the development of ICE 2? And in fact, the development of ICE 2 is ongoing, but it's primarily community supported these days. There aren't many people at JPL whose focus is ICE 2. I'll talk a little bit more about NISAR later, but the development of ICE 3 has really been driven by the need to develop new algorithms for NISAR. And the original developers of ICE 2 felt that that the design of ICE2 didn't really lend itself to the flexibility that they needed to implement these new algorithms, and that it was time to learn some lessons from ICE2 and develop a new library that was sort of a ground up redesign. And there's still a gap in some of the functionality. There's some things that ICE3 can do that ICE2 doesn't do, and there's ICE2 has a long history with lots of sensor support. So there are definitely features in ICE2 that are missing in ICE3. So there's not a perfect one-to-one correspondence, at least yet, in terms of capabilities, and I can talk a little bit about that a little bit later. But the main goal of ICE3 is really just to implement a more modular and extensible structure to be able to have some more flexibility to be able to support not just you know, end-to-end workflows to process SAR data, but to be able to build new custom workflows and support more advanced algorithms in future SAR missions. There's also lots of improvements to documentation and testing, I think, and much more leveraging of GPUs for hardware acceleration in a lot of these SAR processing algorithms. As I mentioned, ICE3 is open source. This is keeping with a big push at NASA these days towards open science, which really means open source code, open and freely accessible data, and trying to sort of foster a community that's more transparent and more collaborative towards scientific progress. And the ICE team are really strong believers in this. Our code has been open source for, I think, including ICE2 for decades now. And we're trying to help with this push by, you know, contributing to ICE3, making ICE3 accessible for others to contribute to, also contributing to some of the other tools in the ecosystem. And we're moving more towards trying to engage more with the community. And hopefully have more workshops and have more online discussion. We think this is really important for the SAR community to sort of have this, not just put these tools out there, but also make the source code available and be actually interacting with the community. And the goal is to try to develop, as I think I mentioned, an ecosystem of libraries and tools. So not just have ICE3 be the only tool for processing SAR data, but to make it useful for other tools and other developers and other platforms to try to work collaboratively and yeah, really form a whole ecosystem of tools. And the goal is that can support NASA's own SAR missions in the future, as well as commercial and international SAR missions and the community more broadly towards applications and science usage of this data. And so to really emphasize that, I kind of put together a diagram of some of the tools and platforms and SAR missions out there that are already sort of interacting and have these codependencies between them. So this is including ICE3 itself and some tools that ICE3 depends on, like PySolid, as well as tools that depend on ICE3. You know, the S1 reader and some of the Opera workflows that I'll talk about, and as well as missions like InSAR and platforms like OpenSAR Lab. So I think with all this is a really exciting time for the SAR community to have all of these tools available, and I think there's just room for more growth from here. Getting back into sort of the structure of the code a little bit, I mentioned one thing that's really important about ICE3 is this modular extensible structure that it has. So the way that I think about that is that the code kind of can be organized into layers. And at the lowest layer, you have these low-level data structures and functions that we can compose to make SAR algorithms. So these are sort of our lowest level building blocks. Things like data structures to represent orbit data and attitude data, the position and velocity of the SAR sensor and its orientation in space. Other things like coordinate grids in radar, azimuth range coordinates, or geocoded coordinates like projected coordinates, lat-long coordinates. We have lots of functionality for interpolation in 1 dimension and 2 dimensions, transformations between the different coordinate systems, and lots more stuff, signal processing, filtering applications. And we can compose these low-level data structures that ICE3 provides into modules, which are the middle layer, and they correspond to like SAR algorithms. So we have a module in ICE3 for range compression, another module for time domain back projection, for image focusing, as well as other modules for like geocoding data, interferometry modules, lots of lots more modules besides those listed here. And then at the highest level, we can compose these modules into end-to-end workflows. These are really our product generation workflows or our science application workflows. And so ICE3 itself contains the workflows to generate ISAR products like the RSLC, GSLC, GCOVE, and InSAR products. And then outside of ICE3, in some of these other tools that I just showed in the kind of the broader ecosystem are workflows for generating new products using Sentinel-1 data based on ICE3. So using the ICE3 modules and data structures in new custom workflows to create new products from Sentinel-1. So this is included in ICE3 itself, just part of the broader sort of ecosystem of tools. And to kind of give an example of the Python API and some of the lower level data structures that I'm showing, I thought it would be interesting to show how you might do something simple with ICE3, like compute the line of sight vector from a target on the ground to your radar platform. And so let's assume for this example that we have a SAR product. In this case, we'll use a ISAR RSLC product. And maybe I should introduce, I'm not sure how familiar the audience will be with some of the ISAR products at this point, but the RSLC is a single look complex image in radar coordinates. So in range azimuth coordinates, not in map coordinates on the ground. And so we use this as our SAR product, and we'll assume that we know the lat long height coordinates of our target, and let's get the line of sight vector. So we can go through line by line and kind of see how this works in ICE3. So first, the imports. If you install ICE3, you'll get the ICE3 package itself, as well as another package called ISAR, which includes some of the ISAR specific functionality. And we'll also use a little bit of NumPy here. So the first thing that we'll do is open up our SAR product. So we can pass in the file path of the HDF5 file that contains the ISAR data. We'll open that up as an RSLC. ISAR products in general, will contain multiple frequency subbands. So typically what we call frequency A is the main science band. That's the higher resolution data. And the products will often contain a frequency B, which is a sideband with lower resolution data, most typically used for like ionosphere estimation. But some of the products will just contain frequency B. So a general way of accessing the data in the product that you'll probably want is to get frequency A if it exists in the product, which we're checking here, and otherwise just get frequency B. And the product contains orbit data. So this is telling us about the trajectory of the satellite as it was collecting the data in the product. It also has Doppler centroid information. So this is a very coarse 2D lookup table that tells us about the azimuth frequency centroid of the signal data in the product. And so this will be useful. We'll use this a little bit later on because it tells us about the orientation of the beam centroid as it's collecting the data. And it also has what we call a radar grid, which is the coordinate grid in azimuth range coordinates, and also has some additional information like the look direction of the satellite and the wavelength of the SAR data. So we'll get all this stuff from our product. And then we pass in some longitude, latitude, height of the target, and we'll assume that that's with respect to the WGS84 reference ellipsoid. And so our first useful bit of functionality in ICE3 is the ability to convert from lat long height to a different coordinate system, to an ECEF coordinate system, so a Cartesian Earth-centric coordinate system. So we can use our ellipsoid and do this long lat to XYZ conversion to get the position of the target now in ECEF coordinates. Another really useful tool in ICE3 is this Geo to RDR tool. There's a couple of implementations. So this implementation of Geo to RDR uses a bracketing algorithm. And what it's doing is converting from geocoded coordinates, or in this case, from ECEF coordinates to radar coordinates, meaning azimuth time and slant range coordinates. So we'll pass in our target position in ECF coordinates, the orbit data and Doppler data that we got from the product. And we also need to know the wavelength and the look side of the product. And then we can use Geo to RDR to estimate. So this is giving this the azimuth time coordinate. It would also give us the slant range coordinate. In this case, we're just ignoring that. We don't need that here. And then when we know so this is the time when the target crossed the beam center of the radar antenna. And so at that time, we can interpolate the orbit to get the position of the platform. This would also return to us the velocity of the platform, which we're not going to use here. And now we have the target position and the platform position in the same coordinate system, and we can use that to get the line of sight vector. So I just have a helper function to normalize this so I can get a unit vector in the line of sight direction. And then getting the unit vector itself is really easy. Just get the difference between the positions of the target on the platform and normalize that to a unit vector. Just sort of taking a sidestep here to talk about installation of ICE3. So if you want to use ICE3 today, my recommendation is that you install it from Conda Forge. The ICE3 team makes binary packages of ICE3 available on the Conda Forge channel, and this is by far the simplest and best way to install ICE3 if you just care about using it. So if you have Conda installed, you can just say Conda install, tell it to install from the Conda Forge channel, and tell it to install the ICE3 package. What this will do is, if your machine has GPU capabilities, it'll try to give you the GPU version. If you don't have, if your machine won't support the GPU functionality, it'll just try to give you the CPU version, the CPU only version. But you can also explicitly install either version. So if you know that you just need the CPU version, you can say ICE3 CPU. Or if you know specifically that you want the GPU functionalities, you can ask for the CUDA version. And this will fail if your machine doesn't support it, if you don't have the CUDA drivers installed, or if you don't have a GPU that can support it. You can also install from source. If you plan on contributing to ICE3, this is a good way to do it, would be to clone the repo and install from source. There's a couple of ways that you can do that. The easiest one is just to use pip, like you would with any other Python package. So you can clone the repo and cd into the project directory. I still am going to recommend that you install the dependencies using Conda, which is what we'll do here. So we can just create a new Conda environment using the environment.yaml file that's stored inside the repo, and then activate that environment, and then just say pip install and pass it the current directory to install ICE3. It is possible to install just a side note on that, it is possible to install the dependencies of ICE3 without using Conda. And some people have tried to do that, but it's much more tricky. One thing to keep in mind if you're going to build ICE3 from source is that ICE3 has a couple of compile time dependencies, and as with all compiled code, you want your compiled dependencies to be built with the same compiler toolchain that you're building ICE3 itself with. Otherwise, you could run into ABI issues. You can run into a binary compatibility issues between the different libraries. So a really foolproof way of installing ICE3 from source is to get everything from Conda, from the Conda Forge channel, which is what will happen if you install your environment this way. And then you're guaranteed to have an environment of dependencies that all interact well with each other. Finally, you can install with CMake. If you want something even more low level, that's a little bit more advanced and requires more steps. And I don't go into it here, but there's installation instructions here if you want to tinker with the C++ code and want to use CMake to do that. I mentioned a little bit earlier that NISAR and ICE3 are sort of tightly coupled with each other, that a lot of the development for ICE3, basically all of the development of ICE3 has been mostly motivated by the NISAR mission and the needs of the NISAR mission in terms of algorithm development. So the core development team of ICE3 are all members of the NISAR algorithm development team. It also means that all of the NISAR level 1 and level 2 science products can actually use ICE3 to generate those products. And ICE3 also includes tools for reading the NISAR products. So if you are interested in using NISAR products in your science workflows, installing ICE3 can be a good way to interact with those products without having to interact with the lower level HDF5 interface. I'll just introduce some of the products as a way of kind of talking a little bit more about the capabilities of ICE3 and how it relates to NISAR. So these first two products are the RSLC and GSLC products. We already talked about the RSLC a little bit. These are the single look complex image products in range azimuth coordinates. And then the GSLC is in the geocoded coordinates. So it's geocoded onto a map grid. At the mid-latitudes, these GSLC products are provided in UTM coordinates. At more extreme latitudes, they'll be provided in polar stereographic coordinates. There's also the GCOV product, which is the geocoded polarimetric covariance product. Another product that's provided in map coordinates. This includes the polarimetric covariance terms in gamma naught convention. So here we're showing the same copol data in sigma naught and in gamma naught. And the gamma naught convention is this is called a radiometrically terrain corrected product. So you can kind of see the terrain that's visible in the sigma naught product is sort of sort of flattened out here by the different area normalization in the gamma naught convention. There's also InSAR products. So here I'm showing the unwrapped product. This is the geocoded unwrapped product. There's also a range Doppler or radar coordinate system unwrapped product formed from the interferogram of two input SLCs. And so these products are going to contain the unwrapped phase data. They also contain coherence and some other layers. In addition, there are interferometric products that are that we call the offsets products. So pixel offsets in radar coordinates and again in geocoded coordinates. Here I'm showing the slant range offsets between the two products, as well as the along track offsets between the two products, estimated with two different algorithms. So these products will contain multiple layers using different algorithms to estimate the offsets. Yeah, so as I mentioned, all of the NISAR workflows for these level 1 and level 2 products are implemented in ISCE3. And a neat thing about that is that it means you can use ISCE3 to generate your own custom NISAR products using some custom parameters. So the workflows are very easy to run. They take configuration files in YAML syntax. There's a command line interface to use them. So you could use it like this, say Python and -m to run a particular module. In this case, we're running the RSLC module, which is called nisar.workflows.focus, and you pass in your run config file. And all of the default YAML files are stored in the repository. You can find them at this link. That's a good way to learn about how the workflows are parameterized by default, and also a good way of creating your own custom run config files. You can just grab one of these YAML files and edit it to plug in your own parameters in your own input files. NISAR is not the only project at JPL that's heavily dependent on ISCE3. There's also the Opera project, which may or may not have been talked about earlier in this workshop. Opera stands for Observational Products for End Users or Remote Sensing Analysis. This project is really designed with the goal of creating higher level, more science-ready, analysis-ready products from existing radar sensors. So in this case, ISCE3 is heavily used in the development of two products from Sentinel-1 data. The first product is the co-registered single-look complex product. This is very similar to the NISAR GSLC product. It's a geocoded burst-wise Sentinel-1 product, SLC product. There's also the radiometric terrain corrected product, the RTC product from Sentinel-1, which is very similar to the NISAR GCOVE product. It's in that gamma naught convention. These are both generated using modules derived from ISCE3 in open source code bases that are outside of ISCE3. So the Compass workflow you can find here, which is used to generate the CSLC product, and the RTC software is well named. That's how you generate RTC products. We also have some tools for parsing these Sentinel-1 products into ISCE3 compatible data structures. So if you want to use ISCE3 with Sentinel data in your own workflows, this is a useful tool. This S1 reader is a good way to be able to interact with Sentinel data using ISCE3 tools. So just as an example, here's an example of an RTC product generated from Sentinel-1 using these modules from ISCE3 to do the gamma correction. Not gamma correction. Do the radiometric terrain correction to gamma naught. So this is showing a different copol now in beta naught convention on the left and in gamma naught convention on the right. And so you can see that the terrain is sort of flattened by that different area normalization. Starting to wrap up, just give some insight into the current status of the product, of the ISCE3 code base, and where we kind of foresee going in the future. For now, ISCE3 is still, I would say, in beta status. So some of the API might be subject to change. I would say the library feels very mature now, though. I think we're getting close to a point where we can start stabilizing the API, especially with NISAR data processing going to start soon. So I'd say if you're interested in using the library, keep this in mind that the API is still subject to change. But I think informally, I think that the API has gotten pretty mature and is relatively stable now. We're very excited that we recently migrated all of our development to GitHub.com. So the code base itself has been open source for a long time, but we've had an internal Git repo that we've used for all of our actual development, because the team has been really dependent on on having a continuous integration server to build and test the code as we develop on it. And it's taken us a long time and a lot of effort to finally get that server migrated so that we could develop on public GitHub. So as of, I think, just June this year, very recently, we've migrated everything to public GitHub, and now you can see and interact with the development of ISCE3 as it's going, as we're making changes to the code base. The current focus for now among the core team is still on ISAR. So we're now in the ISAR commissioning phase, and afterwards we'll be entering cal-val phase. So we're going to be calibrating the algorithms and calibrating the instrument and stress testing the algorithms and doing validation of the image data. There's lots of work ongoing on improving documentation, and we want to try to add more tutorials so that ISCE3 is easier to use and contribute to for others, but that's very much a work in progress right now. And then I mentioned at the beginning that there's still a big gap between ISCE2 and ISCE3 in terms of sensor support for non-ISAR sensors. So ISCE3 is where you want to go for ISAR support. There's also now pretty decent support for Sentinel-1, but for other legacy sensors like like ALOS, NVSAT, and for newer missions like biomass, we really hope to be able to add more support in ISCE3, and this could be something that's more community driven. But still, for now, our focus has been driven by ISAR. So hopefully, this is something that we can add and develop more in the future and make this more of a useful tool for the community for processing lots of sensor data.
But there is some support for ALOS-1 data because that's what they've been using for some of the testing.
Yeah, that's right. So we can what we've done for testing for ISAR has been to take L-band data from ALOS and for UAVSAR and to basically repackage it to make it look like ISAR data. So we repackage that data into L0Bs, which I didn't talk about, or RSLC format and process it with ISCE3. So that is possible now. There's some caveats with that, especially in the UAVSAR case. Those UAVSAR sample products are filtered down. There's some signal processing done to those to make them look more like ISAR data. But certainly, yeah, you can. It's possible to repackage your ALOS data and use it with ISCE3 today. My hope is that because ISCE3 at a low level is so generic and is just using these very reusable, flexible algorithms and data structures, my hope is that you won't need to do that repackaging. That we can develop tools to be able to use ISCE3 directly with sensor data without having to make it look like ISAR data.
Yeah, so Forrest Williams, in a project that he is working on for me, has, for instance, used Umbra data and got it into ISCE3 to do the full geocoding and RTC processing workflows. So it's definitely possible. The biggest challenge was actually not ISCE3, it was more because Umbra's data isn't sampled in sort of a range Doppler geometry. So there was some extra work that was needed. Piyush Agram helped out with that a little bit. But if you have a range Doppler sensor type, I think getting things into ISCE3 and using the internal functions is comparably straightforward.
Cool. Yeah, thanks, Franz, for sharing that. So just showing off some of the sort of work in progress documentation. So today, if you go check out the ISCE3 documentation pages, you'll see something that looks like this, with some installation instructions and some API documentation. I'm really hopeful that soon we'll be starting to add some tutorials and make it a little bit easier to get started with ISCE3 for people who are less familiar with the internals of the library. So still a work in progress here, but I think we're making good progress on this. And I'll share, so just list some resources. For ISCE3, you can find the GitHub repo here, a link to the documentation pages, and also we'll try to host discussions. So if you have questions about ISCE3 or if you want to discuss more, this is a great place for that, the discussions page on the repo. And I'll end there. I'll leave up these links, and I'm happy to take questions.
Thank you. There is one question in the Q&A which is about filtering. Maybe you can find it and repeat it.
Yeah, let me see if I can.
What spatially adaptive filter are you talking about in Gamma?
I guess that's ADF, right? So that's probably the
that one.
Yeah, there is a filter that's just called adaptive filter in gamma, but it's, as far as I know, proprietary and not available in source code form.
Okay. Yeah, I figured Jeff wasn't going to know what a gamma adaptive filter was.
Yeah, that's outside of my expertise. I don't
Yeah,
think there are
it's
any
the
adaptive
gamma remote
filters.
sensing software, not the gamma of the radar reflectance.
Right. Yeah, I don't think there are any like adaptive speckle filters, anything like that implemented in ICE3 so far. That hasn't been something that we've needed for any of the NISAR workflows yet.
Yeah,
there
ADF,
might be in some.
Isn't ADF the Goldstein-Warner filter from the
No,
paper?
it's not. It's something else.
Oh.
It's a Werner filter, not a Goldstein-Warner filter.
It's very funny because 2 years ago at IGARS, I was sitting next to Charles Werner at a talk, and somebody brought up the Goldstein-Warner filter, but always called it the Goldstein filter.
Yeah.
It was fun to sit next to Charles for that. Yeah, so that's currently not implemented. It wouldn't be super hard to implement probably a frequency-based adapter.
I think you probably want to keep them in separate conda environments. I think they're not really compatible to be in the same conda environment, but then you can just create a different conda environment.
This is the answer to the next question in the Q&A, if you're confused by the sudden jump in topic.
Maybe it's so I see the chat and it's empty for me. Maybe if I stop sharing.
There's another button down at the bottom that says Q&A.
Ah, okay. Let me see if I can find that.
It was just asking if you do ICE2, ICE3 in the same environment. Or
I see. Okay. Yeah, good question. Yeah, so it's a very explicit intention of ICE3 that you should be able to install ICE2 and ICE3 in the same environment. So that should be supported, yeah. And if you have any problems with that, you should definitely let us know.
More questions. We have a little time.
Just follow up on that. Is it a good idea to have workflows with some of ICE2, some of ICE3? Is that something you are expecting as a use case, or more of a patch while some features aren't in ICE3?
I think it's totally valid as a use case. You might need to do some impedance matching, so the data structures will be different in ICE2 and ICE3. So you might need to there might be some patching that you need to do to convert some data structures to be compatible with the ICE3 data structures, or vice versa. But apart from that, like a little bit of patching, it should certainly be possible.
Okay, thanks.
Mm-hmm. At least for now, let's say you have, different sensor types that you want to combine. You do InSAR with 2 different sensors. You may need ICE2 for one, ICE3 for the other, if NISAR is involved, and then take the products of those, or maybe work with Yunjun to adjust MinPy to adopt them and import them both. And maybe we should say it's a big week, I think, for the ICE3 team also. I think tomorrow is when the first L-band data sets will be collected. I think those are not full scenes, but there's some first testing of processing capabilities, I think, that will happen late this week or early next week for NISAR.
Yeah, there are definitely some exciting commissioning activities going on. I'm not sure exactly what I'm allowed to say publicly about what the milestones are. So I'll
maybe I should just take that back. But we're all excited so far. What's publicly out there and all we know is NISAR is in great spirits and is on task, and so we are really excited to see this come along.
Yes, absolutely.
Why would it be secret?
I don't know. I don't know if it is secret. I don't know exactly, but in general, like making announcements about developments with the instrument is supposed to happen through like the proper channels and not me.
The sequence of events is actually public. It's on a website. The outcomes of those events, I think there's a 2-day sort of wait period for NASA headquarters to have first dibs on responses.
Yeah,
That
and
makes sense.
so headquarters asked us to not release anything until 2 days later without their permission.
But what sort of the sequence of events is, I think, is on a public website. So that's not necessarily a secret.
They did announce the successful deployment of the reflector last Friday, only a few hours after it happened. So if it's important enough, then they approve it immediately. But they just want to, I don't know, as a rule.
But yeah, you better get already with ISCE 3. You have 2 months to install it, or 3.
Yeah, 2.5 months from now, there should be a massive deluge of NISAR data flowing through the system. 75 terabytes a day.
Jeez. I need to buy some new hard drives.
Update your processing cores. Everybody needs CUDA now. It's like it's graphic cards.
Everybody needs AWS accounts, unfortunately.
Well, when the AI crash happens, maybe the instances will become very cheap.
Yeah. Yeah, actually, that's a problem for NISAR, is that the Amazon raised the price on some of their GPU instances. They also made the instances more capable because of the AI demands, but then they got rid of all the less capable instances that the NISAR processing was planning to use. So they had to try to figure out how to more efficiently use the new instances that cost like 10 times as much, but also had like 8 times as many GPUs or something. I don't know all the details, but
Yeah, it was a big pain for us. We planned to do all of the RSLC processing on a particular type of AWS instance, and then at some point earlier this year, they let us know they were sunsetting that type of instance, and we had to move to a different instance type. And the workflow is designed to run on a single GPU, because otherwise you would just be bottlenecked by I/O. You can't feed the GPU. If you have 8 GPUs, you can't feed them data fast enough to make it worthwhile to process on that many GPUs. But those were the only types of instances they were offering that had the kind of like high precision performance that we need. A lot of their cheaper GPU instances are designed for single precision and lower precision machine learning work, which is not really useful for SAR processing unless you have a really specialized processor that can do like fixed precision geometric computation. So there was a big scramble earlier this year to try to figure out how we were going to do the RSLC processing. And it turns out I think the science data system will be able to run multiple RSLC processes on a single AWS instance with 8 GPUs simultaneously.
Good question by Nassif about ionospheric and tropospheric correction. One of the big things that people are excited about for tropospheric correction is thinking about future sensor types that have multiple geometries, that have like a forward-looking and a backward-looking component. You could think of like a combination of 2 satellites that look in an opposing geometry to look through the same atmosphere in different ways, and then be able to basically reconstruct a tropospheric delay as part of the processing workflow. As part of SDC, the Surface Deformation and Change mission study, that was one of the options that was considered to make the next step forward toward better displacement mapping. For ionosphere, I think NISAR is going to bring a big step forward, because it has a dedicated, even at L-band alone, a dedicated setup for ionospheric correction by having 2 different transmit bands at 2 different parts of the 80 megahertz spectrum that's available. And then with LNS band, there's lots of room to develop algorithms that robustly can use that very large frequency spread to come up with really very accurate ionospheric phase maps and improve that correction. There's lots of data in India that lends itself for new algorithm development in that space. In biomass data, biomass operates at P-band. That's a European mission. That's super tricky for ionospheric correction, and they have developed quite nice algorithms, but I'm sure there's room for improvement. And looking at biomass data alone can also spawn some really nice new ideas in ionospheric correction.
I also see a question online about the GPU performance of ICE3 compared to ICE2. As far as I'm aware, there haven't been any rigorous comparisons done on the GPU capabilities of each. Partly, I think, because they have slightly non-overlapping capabilities. I'm not sure exactly which workflows in ICE2 have been GPUized, what components of them. But I think the algorithms in ICE3 that are GPUized might be slightly different. So, for example, there's a time domain back projection processor that's implemented in ICE3 for the RSLC processing, the focusing algorithm. And I don't believe anything like that is implemented in ICE2. And that really heavily relies on the GPU.
Yeah, the ICE2 focusing is just a standard old-fashioned focusing.
Yeah, a range Doppler algorithm, I think.
Yeah.
ICE2 has Topo, GeoJWADR, and AmpCore, I think. GPUized.
Okay, neat. Yeah, there is a GPU topo implementation in ICE3. It would be interesting to see. I should suggest that to Harash to see what kind of GPU performance we get relative to ICE2. Yeah, that would be a good comparison.
And then there's a question about what the advantage is of the reflector type radar antenna design over sort of phased array. And one of them is that go ahead.
No, please go ahead.
You can achieve very large coverage acquisitions at decent resolutions without requiring like a burst-based acquisition approach, using this sweep-SAR concept where you basically can use geometry and timing to sweep across a very long swath with a fairly simple multi-patch sort of TR module, multi-TR module antenna system. So it's a different approach to doing what also TOPS mode is trying to do, is to get to high-ish resolution data at a very wide coverage. And it's in many ways a simpler approach to that goal.
The Rose-L satellite is going to use a very large planar array to do a type of sweep SAR, but with a planar array. But it's going to be have a much more expensive antenna system. That was one of the disadvantages of using only a planar array. Plus, the big advantage of having the reflector is that we can have the two radar wavelengths operating at the same time without using the same reflector.
There's some potential downsides that we'll learn about, I think, as we go forward. The shape of the reflector itself, some chance that it may change with like temperature, etc., and that could possibly affect some of the polarization integrity. But for now, I think that's all under control. It's pretty stiff, but we don't know. Somebody for quantifying the volume of lava flow filling a caldera. Oops. And estimate diffusion rates. NMX is. So Belay is asking about, can you use backscatter information to look mostly at topographic changes? And in theory, you can. There are some papers that have used repeated acquisitions in the same geometry to look at backscatter changes to sort of see filling of lava flows or building of lava domes. You get different layover and different shadow behavior and different sort of response if the topography changes dramatically. So there are methods. There's a good paper by the team around Zhonglu from what is it, Southern Methodist
SMU.
University. They've done some work. There's also one from UAF, from Ronnie Garpentine's team, that have used this. These approaches are similar to like shape from shading, if you want. So they basically relate variations in brightness to variations in topography, and they work, but their accuracy is limited to probably the 5 to 10 meter range, but they exist. So if you want, you can post on Slack, and I can link the two papers that you can look into. But that is a gap still in science. And one of the NASA mission studies, what is that called? STV, surface topography, and no, is that it? And vegetation.
Surface topography and vegetation.
One of the goals is to build a mission that provides more routine and updated TMs. TM time series is a gap, I think, still in our science.
I think the pace of questioning has slowed, and we are very close to like 2 p.m. Maybe this is an opportunity for you, Franz, to clarify the homework situation one final time.
Oh, yeah. So for oops, my window. Yes, for the ICE Velocity notebook, basically what I would expect that you submit a notebook that's completed, where you poke at an interesting site that you care about. In the notebook, you could add a little text cell that sort of explains what you're seeing, but mostly it's to ensure that you ran the notebook all the way, and you experimented with different locations, and in the velocity time series that was created. So there's no additional programming needed. I think most of you were able to. There were a couple of people that had some issues with widgets, I think. And we'll try to sort those out.
And I think we're done for the day. So thanks to Jeff for coming in and showing us the things.
Thank you.
Thanks to everyone for participating today and asking questions. And some of us will be on office hours tonight at 5, and the rest of us probably tomorrow. See you then.